ನೋಡಿದ್ದಾರೆ ಇಲ್ಲ ನಾವು ಅದು ಇಷ್ಟು
Indian tea.
Night. Good morning.
Good morning, sir.
How are you, madam?
I'm fine, sir. How are you, sir?
Yeah, fine, doing well.
All ready for your
Yes. Good morning, Samrat. Dr. Kuwar. Where are you both guys? Patil madam. Hi, good morning, madam.
Good morning, sir. Good morning, sir. Very good morning.
How are you?
Fine, sir.
How is that? Sir is joining today? Samrat is joining today?
No, sir. He is out of station. You, he will see the YouTube.
sir. Your voice is coming as an echo, sir. Slight echo is coming.
Okay, I'll try to reduce it. How? ಬುಕ್ ಮಾಡಿದ್ದೀವಿ ಆಮೇಲೆ ಇದು ಶ್ರೀಕಾಂತ್ ಕಳಿಸಿ ಅರ್ಜೆಂಟಾಗಿ ಇಕೋ ಆಗ್ತೀನಿ ಅಂತ ಹೇಳ್ತಾರೆ ಒಂದು ನಿಮಿಷ ಸ್ಟಿಲ್ ಇಸ್ ಇಕೋಯಿಂಗ್ ಮೇಡಮ್ ಸ್ಟಿಲ್ ಇಕೋಯಿಂಗ್
No, sir. Not much now. Now it is clear.
ಓಕೆ ನಾ
It's clear, sir.
but I can sort out that problem. If it is echoing is there, let me know.
Recording ಇದೆ. Yes, sir. Recording.
Sir, am I audible?
Yes, sir. Yes.
I think you should come a little closer to the mic, sir. You're a little far off from the mic.
No, if I come nearer, then it will echo is there.
There.
Now it's okay.
Not yet.
Hello. Sir, am I audible?
Yes, sir. But little echo is there. Sir.
Sorry?
Little echo is there, sir.
Okay.
Radhika madam, good morning.
Good morning, madam. Good morning. How is the weather there, madam? Is it raining there?
No, but it's cloudy.
Madam, now you check. Girish. No, ask him to come, not that. Is it? Madam, am I audible now?
Yes, sir.
Echoing is there still. I will try to rectify it.
Okay, sir.
Now it's okay?
Yes, sir. Shall we start, madam? Sir, shall we begin?
Sure,
Yes,
sure.
Shall we begin, sir?
Sure.
Okay. A very good morning to all the people who have gathered today. I must really congratulate the Jabin College staff, principal, and students for eliciting so much of enthusiasm among the students to join and understand the implications of nanotechnology. I welcome you all once again for a very interesting session going to be held first by Dr. C.V. Yellamgad, followed by Dr. S. Krishna Prasad. So we will directly launch into Dr. C.V. Yellamgad's lecture. Before that, I should tell all the people who have gathered, all the audiences present here. In fact, Dr. Yellamgad is the brain behind this entire program. It was his, it was his brainchild. It was his idea which got implemented, and you are able to reap the fruits of this particular great online seminar. So he is one person. I know all of you also know about him as a professional scientist in Center for Nano and Soft Matter Sciences. But apart from that, what you must know, he is also a very enthusiastic and a very clear teacher. He he has these two professions going side by side, as I have learned. In fact, Dr. Srimati Leena will be able to tell you in detail a little later. He's a great teacher and a very good human being, I should say. A very nice human being where his only aim is whoever comes to him, he will be there with a helping hand. I feel that all the people who have gathered here must understand that these are some of the takeaways, children. We know that a person's profession is one thing, his skills are another, but a person, the actual person in a human being, is also an extremely important takeaway. All the children whom we expose, whom we try to expose these great personalities, must also imbibe these kind of humility, helping nature, always ready, and the best thing is extreme hard work. He's a worker alcohol, always at the desk. Time is, he doesn't allow the time to decide when he should stop. He allows the work to decide when he should stop. So I request Srimati Leena Hublikar, lecturer in Jabin College, to do a formal introduction of Dr. C.V. Yellamkar. Over to you, Leena.
Thank you, ma'am. Very good morning, sir. Good morning, ma'am. And good morning to all of you there. I, Srimati Leena Hublikar, Assistant Professor, Department of Chemistry, privileged to introduce today's guest speaker, Dr. C.V. Yellamkar, sir, Scientist, Center for Nano and Soft Matter Sciences, Bengaluru. Dr. C.V. Yellamkar obtained his PhD degree from Karnataka University, Dharwad, and pursued his doctoral research at the Department of Organic Chemistry, Indian Institute of Science, Bengaluru, and Department of Applied Chemistry, National Chiao University of Taiwan. He has been worked as a scientist at Center for Nano and Soft Matter Sciences, Bengaluru since 1997. To have a look at the alchemy of his achievements in the field of soft matters, nanomaterials, and nanosoft composites with related streams, Sir published his research publications over 200 with a H-index of 37 and over 4,000 citations. Really, hats off to you, sir. Sir has 11 national and international patents to his credits and presented over 300 invited talks and also written reviews in textbooks also. Reviews and also in textbooks. Many of the feathers are there in his crowns of achievements, really. To examples in the field of the government, also in the national and international awards, and also in the field of fellowships. To add a few, in the year 2000, Japanese government fellowship, that is called a Japanese Science Technology Agency, JST, and in the year 2002 and 3, Japan Society of Promotion of Science, JSPS fellowship also. Going to the next one, Sir had also a Government of Karnataka's Sir C.V. Raman Young Scientist Award in the year 2005, along with a Royal Society London visiting fellowship for his achievements in the year of 2007. The Market Research Society of India, that is MRSI medal for the year 2019 is been obtained by Sir. And in the same year, Sir is also awarded with FRSC, Fellow of Royal Society of Chemistry, RSC, from Royal Society of Chemistry, London, UK. And in the same year, in this year, that is 2021, Sir achieved the Chemical Research Society of India, CRSI, medal, and also become an executive member of RSC, a Deccan section. Not the least, Sir has been a distinguished personality among 2% scientists in the World Scientist Global List, which was compiled by a prestigious Stanford University. With this brief introduction, I present before you Dr. C.V. Yellamkar, sir. Thank you for this opportunity.
Good morning, everybody. Good morning, ladies and gentlemen.
Good morning, sir.
Can you hear me?
Yes,
Yes,
sir. Loud and
My
clear.
screen, can you see my screen? Is it shared?
Yes, yes, we can see it clearly.
Once again, good morning, ladies and gentlemen. Dr. Radhika, thank you very much for very kind words, and also Dr. Oblikar for giving me, for introducing me to the audience. At the outset, I would like to express my deep sense of gratitude to the Royal Society of Chemistry, local section Deccan, India, Center for Nano and Soft Matter Sciences, Bangalore, and KLE Society's very prestigious college, PC Jobin Science College, Hubballi, for giving me this wonderful opportunity to participate in this 2 days online seminar on nano and soft materials for societal needs. Well, as I already declared, today I'm going to speak to you on my favorite topics entitled liquid crystals, the unique state of matter. In fact, I should refer to it as 4 states of matter. In this particular presentation, I'm going to cover the fundamental aspects. Here, I'll try to convince you that without the existence of this state of matter, none of us, none of the living systems could have existed on this earth. I shall repeat on this very important point. If liquid crystals were not to be there on this earth, none of the living system could have existed on this earth. With this very important note, let me proceed. Before I proceed with my actual presentation, I would like to say something about my organization where I'm serving. This particular organization called Center for Nano and Soft Matter Sciences, then it was Center for Liquid Crystal Research. This was established way back in 1991 by a great physicist called Professor Shivaramakrishnan Chandrasekhar, FRS, who was an outstanding physicist. In fact, he was the one who discovered discotic liquid crystals. Those can be used in solar cell fabrications. You are also aware of the great person, a great physicist, Sir C.V. Raman, who got Nobel Prize in 1930 because of his discovery of Raman effect. You are also aware of the fact that there is one more Chandrasekhar, Subramanya Chandrasekhar, who is an astrophysicist. He won the Nobel Prize in 1983. I'm very proud to be associated with this particular research organization because this was established by Professor S. Chandrasekhar, who in fact is a nephew of Sir C.V. Raman. Professor Chandrasekhar, who established this research organization, is CVR's younger sister son. Another Chandrasekhar, who won the Nobel Prize in 1983, is a nephew of Sir C.V. Raman, that is his brother's son. So in fact, just to let you know that Professor Chandrasekhar, who established this research organization, is also coming from Sir C.V. Raman family. Now, if I try to put a beta on them, you can see they're all identical. You can see the nose of Sir C.V. Raman and Chandrasekhar and Subramanya Chandrasekhar. They're all coming from the same family. Therefore, I'm really very proud to be associated with this particular research organization. You know, I worked with Professor Chandrasekhar for more than 17 years or so, and whatever I've learned so far, it's all the credit should go to Professor Chandrasekhar. Okay, right from beginning, right from 1991, our research organization is focusing on the molecular design, synthesis, and characterization of liquid crystals. Those can be used for the display applications as well as for the fabrication of solar cells. In recent times, we have been also focusing our attention on gels. And those gels can be used for the fabrication of liquid crystal display. Recently, during about last 5-6 years or so, when Professor Kulkarni joined as a director, then we shifted onto other dimensions of the research, that what we are trying to do is nanomaterials. You know that nanomaterials have, yesterday you must have heard about it, nanomaterials have n number of fascinating properties, especially their optical properties are really notable. On the other hand, liquid crystals. Liquid crystals also have n number of properties, very exciting property. Today I'm going to talk about that a little later. Nanomaterials and liquid crystals, these are the two functional materials. Now imagine when I try to combine them, so you should be able to get what are known as soft nanocomposite. Once you combine nanomaterials with liquid crystals, you are going to end up in getting composites. They are called nanosoft or soft nanocomposites. So these composites exhibit the properties of both liquid crystals as well as nanomaterials. So right from the beginning, we have been focusing our attention on the molecular design, synthesis and characterization of natural synthon-based, economically feasible, conventional and non-conventional liquid crystals, nanomaterials, and liquid crystal nanomaterial composites for both fundamental research and applied science. Okay, right from the beginning, inception of the center, we have been focusing on the calorimetric liquid crystals to develop liquid crystals for the liquid crystal technology, that liquid crystal display. And also we have been working on solar cells. So for the fabrication of solar cells, we are coming up with new viscotic liquid crystals. They are referred to as supramolecular systems or fluorescent viscotic liquid crystals. We have been also working on functional liquid crystals. Now we have liquid crystals A and B. Liquid crystal A has a particular function and liquid crystal segment B has a particular function. Now A is being combined with B. So now I'm going to end up in a molecule or a molecular system where the properties of A as well as B are reflected in the resulting molecule. Like that, we have achieved a lot in this particular area of research work. We have been also working on what are known as banana-shaped liquid crystals. Since the shape looks like banana, they are referred to as banana-shaped liquid crystals. The interesting aspect of these liquid crystals is that although there is no molecular chirality, but when they self-assemble, they give rise to a macroscopic chirality. That's quite interesting. Now, if you want to make ferroelectric liquid crystal display, this can be used, and there will be no cost. I mean, the cost will be minimum. So we have been also working on sensors. As I said, we are trying to develop soft nanocomposites so as to design and develop sensors where these soft nanocomposites use as an active media. We have been also trying to develop sensors for the detection of toxic metal ions, toxic gases, and explosives. Quite interestingly, we have been able to develop electrocatalysts. For example, in the days to come, about 20 years or 30 years later, we'll be running out of the fuel. What we are trying to do is you try to develop an electrocatalyst, and that electrocatalyst can be used to split water. Now, this water can be split into hydrogen and oxygen. Hydrogen acts as a fuel, whereas oxygen is environmental friendly. So we have tried to develop this kind of electrocatalyst, and to some extent, we are quite successful. This particular work is being patented as well as published. Okay. What is matter? Let me go through some fundamental aspect quickly. Teachers may have to forgive me because I'm addressing BSc students. I just would like them to recall what they have learned during the SLC level or so. So what is matter? Matter is everything that around you. Matter is an object that occupies space and has a mass. It can be visible or invisible. Matter is made up of atoms, group of atoms or molecules. Why matter exists in different states? It's because the correlation between the constituent atom is different. Therefore, you tend to get on this earth, you have different states of matter. Okay, right from our school days, we have been made aware of the existence of different states of matter: solid, liquid, gas, and plasma. In addition to these four states of matter, there exists another state of matter called liquid crystals. Ladies and gentlemen, from today onwards, you should add to your memory that in addition to 4 states of matter, solid, liquid, gas, and plasma, you should know that liquid crystal is yet another state of matter. Solid is independent state of matter, likewise liquid, gas, and plasma. As all of you are aware and you have studied well that solids, they have their own set of properties. For instance, solids never flow, they fall. Whereas liquids, they flow, but they never fall. So solids, they never flow, whereas liquids flow. So these are the contradicting properties of very interesting properties of solid and liquid. I don't see any solid. If you know, let me know, or anyone of you know that solid never flows, it falls, whereas liquid flows. Okay, like that you have a n number of properties of gas and plasma. Likewise, you have liquid crystal state of matter, which is a 4th state of matter. They have their own set of properties. Given the very fact that liquid crystal exists between solid and liquid states of matter, they possess the properties of both liquids as well as crystals. I shall come to that point a little later. Once again, liquid crystal state is yet another state of matter, and it is called unique state of matter given the very fact that it has n number of interesting properties. Those properties are coming from either solid or liquid. Ladies and gentlemen, there exists another state of matter called Bose-Einstein condensate. Now, if I ask you to tell or let me know what are the states of matter from today onwards, you must say that Bose-Einstein condensate is a low energy form of matter. It was discovered in the year 2003 and it was published in Science Journal in 2003 itself. Okay, we have Bose-Einstein condensate, solid, liquid crystal, liquid, gas, and plasma. Today, I'm going to talk about the unique properties of liquid crystals. All right. As I told you, right from the beginning, we have been made aware of the existence of 3 states of matter: solid, liquid, and gas. All of you are aware of the fact that solid, when melts, it goes to liquid. When liquid vaporizes it, converts into gaseous state. Now, this can be reversed. So if you condense gas, you'll get the liquid, and if you freeze the liquid, you'll get back the solid. Now, please understand what's happening here. As you go on increasing the temperature, a solid can be converted to liquid, liquid can be converted to gas. Here, the energy is increasing or the temperature is increasing and therefore energy is increasing. Now, when you talk about density, solid are more dense than the liquid and liquid are more dense than the gas. I hope you agree with me. All right, ladies and gentlemen, now we have to think of adding one more state of matter. Well, the conversion of solid to liquid, liquid to gas, gas to liquid, or liquid to solid, this is what is known as a phenomenon, phase transitions. Now, we have to introduce a liquid crystal state of matter between solid and liquid. Okay, in order to understand what are liquid crystals, which is the 4th state of matter, which is present in your body completely, not only you, anything that exists on this earth as a living being or any living thing that exists on the earth is comprised of liquid crystals. If you take anything, you start with unicellular system or bicellular system, a tricellular system, or a polycellular system, or multicellular system, whatever you want to call. We are multicellular systems. We human beings are composed of n number of liquid crystals. So without that, I don't think there is anything exists in our body. I shall come back to that point, interesting point a little later. Well, now in order to understand what are liquid crystals, it's quite essential to understand what are liquid crystals. We must understand liquid crystal because that forms the basis of your life. In that case, you must understand what are liquid crystals. Well, that's one aspect. Now, whatever mobile phone you have, all of you are watching mobile phone now, as I understand. All of you are watching because of liquid crystals. You have mobile phones right in your hand and you are watching my presentation. So there you get a small panel called liquid crystal display. So I don't think it's easy to be in this present era without the help of liquid crystals in the form of liquid crystal display. All right. In order to understand what are liquid crystals technically, we need to understand the important properties of crystals and liquids. I shall not worry about the gas and plasma or bosons and condensate. I shall repeat what I said. In order to understand technically what are liquid crystal, you must know the few important properties of solids and liquids. All of you know that solids are broadly classified into two categories. One, amorphous solid, another is crystalline solids. So crystalline solids can be further divided into two classes. One is called isotropic crystals and this anisotropic liquid crystals. Sorry, anisotropic crystals. Now, as far as the liquid crystals are concerned, I would like you to focus on the properties of anisotropic crystals. In general, solids or crystals are made up of atoms, molecules, ions. In that system, these are arranged rigidly. A large intermolecular attractive forces hold them together, as are shown here, schematically. They have crystallography distinct axes and interact with light in a manner that is dependent on the orientation of the crystalline lattice with respect to the incident light. Now, let us not worry about anything. Try to understand the few important properties of given crystals, especially anisotropic crystals. They possess positional order, orientational order. They maintain their shape. They do not flow. They cannot be compressed. They show what is known as birefringence. I shall repeat. You take any solid, they possess positional order, orientation order. They maintain their shape. They do not flow. They cannot be compressed, and they are birefringent. Okay. In the context of understanding what are liquid crystal, you, my dear students, please note down 2 points. One, given crystals, they do not flow. I shall repeat. Please note that given crystal do not flow. I hope you agree with me. And another important point is birefringence. Okay, given solid or anisotropic crystal, it doesn't flow. Sorry, it doesn't flow. It has birefringence. There is no flow, but it shows birefringence. So what is birefringence? Birefringence is nothing but the measure of the magnitude or double refraction. All of you are aware of the phenomenon called refraction of light. It's the bending of light ray when it travels from one transparent medium to another. The change in speed causes the direction of the light to change. Now you hold a glass of water, or you take a glass, fill it with half with water, and then put a pencil. It appears as if the pencil has bent. That is not the case. Pen has not broken, so the pencil has not broken. It is the bending of light that gives you this kind of a phenomenon. What is birefringence? It is a double refraction. Double refraction, it is the bending of refraction, or it is a bending of light ray into two different directions. When it travels through an anisotropic birefringent media such as crystals, it is okay. It is a result of splitting of incident light into two rays. One is called ordinary beam of light and extraordinary beam of light. Simply try to understand that the square what I have shown is a birefringent material. This is, please consider this as a birefringent material. When an ordinary beam of light passes through this anisotropic medium or crystal, the incident beam of light gets split into two. One is called ordinary beam of light, another is called extraordinary beam of light. I shall repeat. When an ordinary beam of light is made to a birefringent material, the incident beam of light gets split into two. One is called ordinary beam of light, another is called extraordinary beam of light. For example, light beam passes through this, the incident beam of light gets into two. One is ordinary light and extraordinary light. They differ in their velocity. Okay. Now you are able to see two images of pencil. One originates from the ordinary beam of light, whereas the other one originates because of the extraordinary beam of light. Now, quite interestingly, if I rotate the crystal, the image which originates from the ordinary beam of light remains stationary, whereas the image originating from the extraordinary beam of light rotates with the angle with which you rotate. I shall repeat. I have taken a pencil. I have taken a crystal which is anisotropic, shows birefringence, and light is falling on that. The incident beam of light gets split into ordinary beam of light and extraordinary beam of light. Therefore, you have two images. One called one is originating because one originates because of the ordinary beam of light, another originates because of the extraordinary beam of light. So, in essence, what is birefringence? Birefringence is nothing but the magnitude of double refraction, or it's a double refraction in the sense when you take a birefringent medium and pass an ordinary beam of light, the incident beam of light gets split into two. One is called ordinary beam of light and extraordinary beam of light. I have given you the example of calcium carbonate. Well, no, let me tell you the quite interesting things. In your day-to-day life, you use plastic materials, different types of plastic materials. They should be transparent. I intend to say that in your day-to-day life, you use a n number of plastic items, including polyethylene bags. They are transparent. They are called stressed or stretched polymers. So these stressed or stressed polymers are nothing. They show what is known as birefringence. So this phenomenon you can realize it using plastics. You take any transparent plastic which is stressed or stretched, they show what is known as birefringence. In that case, how to test it? Well, now you have a scale in your compass, you have a scale. You have different items in the geometrical box. All of them are birefringent. Let's forget everything. Just take the example of scale. If you take a plastic scale, which you use in your day-to-day life, okay, while studying, that is birefringent. Now, when I say so, I should demonstrate whether the given scale is, I'm saying it is birefringent, means when an ordinary light is made to pass through this scale, the incident beam of light gets split into two, you will get an ordinary beam of light and extraordinary beam of light. There is a way of testing it. Well, I give a scale to you. You have to tell me whether it is birefringent or not. Okay, in general, if I give you a transparent medium, okay, then you should be able to tell me whether it is birefringent or not. Okay, there is a way to test using polarizer. So, okay, all you know that ordinary light is also known as unpolarized light. Ordinary light means what? It can be tube light, it can be candle light, it can be sunlight, whatsoever. So that light, what is around you in your day-to-day life, it's called ordinary beam of light. There you know that a light wave that is vibrating in more than one plane is referred to as unpolarized light. When such an ordinary beam of light is made to pass through what is known as a polarizer. This is a polarizer. I think most of you have heard about polarization of light. So when an ordinary beam of light is made to pass through a polarizer, what happens is that, I think most of you know, that the vibration of light wave gets confined to a single plane. That is, this phenomenon is known as a plane. This phenomenon is known as polarization of light. So this light which is coming out of this polarizer, this is a horizontal polarizer. Light, what you are getting is known as plane polarizer light, and it's a vertical state. Okay, now you have two. Okay, now if you use vertical polarizer, as shown here, you pass a beam of light through vertical polarizer, you tend to get vertical state. Now, if I take the same polarizer, is a vertical polarizer, if I rotate it by 90 degrees, it becomes a horizontal polarizer. Now you have vertical state and horizontal state. Using only one polarizer, I can either get vertical state. Now, if I rotate it by 90 degrees, this polarizer, then I'll get a horizontal state. Or you can use two different polarizers, put it one vertical state and one another horizontal state. So now using these two polarizer, one has a vertical state, another has a horizontal state. Then let's see what happens. So vertical state, and where I'm going to use vertical state polarizer, the polarizer which gives me vertical state and the polarizer which gives me horizontal state, I can show whether the given material is birefringent or not. Okay, now here it is. Okay. Okay, a light passes through means you take one polarizer, horizontal polarizer, take another horizontal polarizer, you cross, light would emerge, means light passes through. Now, interestingly, when you take a vertical polarizer, take a horizontal polarizer, cross them. So this is a horizontal arranged. This is a polarizer giving you horizontal state. This is a polarizer giving you vertical state. Now, when you cross them, take a horizontal polarizer and take a vertical polarizer, cross them, then light would not emerge, as you can see here. So this complete dark, what you say, is resultant of the vertical polarizers. So one polarizer is being taken, horizontal polarizer, vertical polarizer being put on the top of that, then you don't get to see light. Okay, this is a horizontal polarizer is being made overlap on the vertical polarizer. So therefore, where there's a crossing, you don't get light. So light won't pass through between. The whole idea is, our whole phenomenon is, when you try to send beams of light through cross polarizer, light would not emerge. I shall repeat, when you try to send a beam of light through cross polarizer, light would not emerge. Light will not be coming out. Now, interestingly, when you take a crystal, anisotropic crystal, I refer to it, you know that crystal just now figured out few interesting properties. A given crystal never flow. A given crystal never flow, but it shows birefringence. Now, when I put a given crystal, you can take any crystal. Say, for example, take benzoic acid crystal. So if you take a benzoic acid crystal, okay, when you put between the two cross polarizer, you can see the light is coming out. So because this light comes out because the anisotropic crystals have interesting properties, means they are birefringent. This light, what you see, is because of the existence of the extraordinary beam of light. Because of the interference of both the waves, you do get the light here. So if you take any anisotropic crystal, put between the two cross polarizer, you get to see light. In other words, it's very simple. You take your scale, okay, your geometrical scale, and put between the two cross polarizer as shown here, you get to see beautiful light. So this is nothing but birefringence of a given material. As I said, you take any plastic items which you use in a day-to-day basis, which should be transparent. When you put between the two cross polarizer, you definitely get to see this color, okay, as shown here. All right. Now, so far you have tried to understand. Please recall what I said. I said I requested you to remember two important points as far as the anisotropic crystals are concerned. Crystals never flow. Crystals never flow, but at the same time, they show what is known as birefringence. Yes, solid, no flow, but birefringence. Okay, now liquids. In liquids, molecules are loosely held and diffuse randomly. Weak intermolecular force, attractive forces exist in these systems. So in liquids, unlike in solid, if you check solid and liquid, the mobility of the molecules, how it looks like this. So there is no position order, there is no orientation order. They do not maintain their shape. Their flow is most important. If you talk about solids, there is no mobility, there is no flow. But when you talk about liquids, there's a mobility, there's a flow. They cannot be compressed and they are not birefringent. So now quickly, let us compare the properties of solids and liquids. Solids, they have orientation order and position order in 3 dimensions. They are birefringent, okay, and no flow. Now, therefore, when you put anisotropic crystals or solids between the 2 cross polarizer, you tend to see light. Ladies and gentlemen, you must understand a point here that if you take a solid between the 2 cross polarizer, you get to see color because of the birefringence, but there is no flow. Solids, birefringence, yes, flow, no. On the other hand, if you go to liquids, there is no position order, there is no orientation order, therefore there is no birefringence, but they are fluid. But obviously, your answer will be the same as I say now. If you put liquid or water, coconut oil or cooking oil, whatsoever, between the 2 cross polarizer, you don't get to, light will not emerge because they are called isotropic systems. Okay. Now quickly, solids, no flow, birefringence, but liquids flow. Yes, they flow, but there is no birefringence. Then what are liquid crystals? With this background, let me define what are liquid crystals. I want to bring back those 2 important points. Solids, they do not flow, they show birefringence. On the other hand, liquids, they flow, but they do not show birefringence. Ladies and gentlemen, liquid crystal is a unique state of matter. They flow like liquids. They flow like liquids. At the same time, they exhibit what is known as birefringence. Okay. So let me show this slide, very interesting slide to you. Now recollect: solids, orientation order, position order, birefringence, no flow. On the other hand, liquids, no position order, no orientation order, no birefringence, they are fluid. Now, if you look at liquid crystals are the intermediate state between the liquids and solids. They do have orientation order. My dear students and my faculty members, so far in liquid crystal science, so far 53 different liquid crystal states have been discovered so far. 53. Okay, all of them, they necessarily possess what is known as orientation order. In addition to that, they do have position order in 1 or 2 dimensions only. If it reaches to 3rd dimension, you will go back to the solid. And they are fluid and viscous. Please note that first 3 properties, orientation order, position order, birefringence, they're coming from the solid, whereas the fluidity and viscosity is coming from the liquids. As you can see, liquid crystals are the intermediate state between those of the solids and liquids. Therefore, they possess the properties of both solids and liquids. Solid properties are orientation order, position order, and birefringence, and they flow like liquids, and obviously they are viscous. In essence, liquid crystals are the intermediate state between those of the solids and liquids. Therefore, they possess the properties of both solids and liquids. So therefore, they show the properties of both solids and liquids in a manner, I would like to put it in a very simple manner. Liquid crystals flow like liquids. At the same time, they show birefringence. Okay, now you can see here I have shown a picture here. A liquid crystal state between the 2, it has been put between the 2 cross polarizer. It is flowing as well as it is showing birefringence. I shall repeat what I'm showing here. Here I have shown, I'm going to play a video. This is called a pneumatic liquid crystal. This pneumatic liquid crystal phase is being used in display technology. Whatever display you have in your hand, they use pneumatic liquid crystal. So this pneumatic liquid crystal has been put between the 2 cross polarizer. When I play the video, you'll get to see the color as well as mobility. Now I'm heating it to isotropic state, means I'm taking liquid crystal state to isotropic state. So you see that when there is a transformation from the liquid crystal state to liquid state, the color would vanish. You can see this. I can see. So this is the liquid crystal state. There is a birefringence. They are moving. When you see this, this is a liquid state. Okay. I shall show you one more. Yeah, this is liquid crystal state between the two cross polarizer. You are able to see fluidity as well as birefringence. Okay, here is one more melting of a pneumatic liquid crystal into the pneumatic. Sorry. Okay, you can see this. Yeah, this is a liquid. There is, ladies and gentlemen, there is no single liquid on this earth under normal circumstances gives you this color when you put between the two cross polarizers. Liquid crystals being birefringent and they move, they show the fluidity property. You will be able to see the fluidity, the mobility, as well as birefringence when you put between the two cross polarizer. All right. So, okay, in essence, liquid crystals, they flow like liquids. They show birefringence like those of crystals, and they are optically anisotropic. They possess orientational order. They possess positional order in 1 or 2 dimensions only. Okay, liquid crystals. How much time I'm left with? Organizers. Hello.
Sir.
Hello. You are able to hear me?
Yes, sir. Yes, sir.
Yes, sir. Another 15 minutes, sir.
All right. All right. Nice. Very nice. Okay. Liquid crystals, unlike other states of matter, truly it is a unique state of matter. Okay. I'm sorry. Okay. Liquid crystal is a unique state of matter. This particular state of matter is called unique because, as I demonstrated just now, they flow like liquids, but at the same time, they show birefringence. As I mentioned to you, there is no single liquid on this earth. You take petrol, diesel, kerosene, water, oil bath, you take any liquid that exists on the earth, they do not show birefringence, but they flow. Liquid crystal is such a state of matter. It is such a state of matter. It shows the properties of both. It flows, but shows birefringence. So therefore, it is referred to as a unique state of matter. The term liquid crystal was coined in 1888 by Professor Otto Lehmann, a German physicist. You can call liquid crystals as ordered fluids or birefringent liquids. Generally speaking, liquid crystals can be classified in 2 categories. One, they're called lyotropic liquid crystals and thermotropic liquid crystals. Ladies and gentlemen, all of us, not only we, it could be anything. You start from a unicellular system, go to bicellular system, tricellular system. We are a multicellular system. All of us are necessarily made up of what are known as lyotropic liquid crystals. You start with a unicellular system. That unicellular system has a lyotropic liquid crystals. So all of us are composed of lyotropic liquid crystals. Very, very important point to be noted. I shall repeat this important point that it can be anything on this earth. We can start from amoeba to dinosaur. All of them are, it can be plant, it can be anything that lives on this earth. They have liquid crystals. I shall demonstrate little later that all of you are composed of n number of liquid crystals. Okay, as far as lyotropic liquid crystals are concerned, that is something to do with life. Without that, we cannot exist. On the other hand, we have thermotropic liquid crystals. These thermotropic liquid crystals, I just now mentioned that these thermotropic liquid crystals are used to fabricate liquid crystal display. All of you are having this mobile phone with you, and you are seeing, you are watching my presentation, and you are able to hear, especially watching through the small panel called liquid crystal display. Is there in your mobile phone? Here we are using thermotropic liquid crystals. Okay, right. Science of liquid crystal is a multidisciplinary one. It requires conception technique from the chemistry, material science, solid state physics, electrical engineering, chemical engineering, biophysics, and so on. Right? But the main contributor to the science and technology of liquid crystals are synthetic chemists. I'm organic chemist. I do the molecular designing and synthesis. Physicists and engineers. Physicists and engineers put together, they have been able to come up with so many interesting devices. All right. This is the most important slide as far as the liquid crystals are concerned. Liquid crystals are known to be the most soft and delicate states of matter. They're extremely sensitive to external stimuli like light, sound, temperature, pressure, electric field, magnetic field. To give one best example, you may be carrying a water bottle. Nowadays, the pandemic situation, everybody carries his or her own water bottle. During the entire day, when you come to the college at 10 about 10, it will be water is okay. But when you are close to 12 o'clock or 1 o'clock, there will be a change in the temperature. So your water molecule gets heated up, but nothing much happens. And till you are there till evening. Means in a day, there is a variation in temperature. As far as solids are concerned, liquids are concerned, nothing much happens noticeably to your eyes. But as far as the liquid crystals are concerned, when if there is change in temperature by 0.001 degree, they change their properties. For instance, if you take your your mobile phone outside, stand in the sun for just for a while, you are not able to see the images properly, because liquid crystals which are present in the liquid crystal state, they go to liquid state. Therefore, you don't get to see the images properly. Now, suppose that in front of me, I have LCD display. Okay. Now, if I try to heat it, with a hot air gun, my screen would go bad. My screen would vanish. Okay. So, liquid crystals are extremely delicate. If you increase the light, or even if you cough, they change their orientation. Anyway, the temperature is obvious. So, what I intend to say is, unlike other states of matter, solid or liquid, liquid crystals are extremely soft and delicate state of matter. Your brain is full of liquid crystals. Okay, you imagine sitting in AC room. I'm sitting now in AC room. My moods are different. I'm very pleased and I'm okay with my mood. Okay, the moment I go from this room to, say, exposed to hot sun, you will get irritated, because the liquid crystals which are present in your brain, now they are going towards they are perturbed. Therefore, there will be change. There is some change in your brain, in your body. Therefore, you are not comfortable. All right. Although they are extremely soft and delicate state of matter, ladies and gentlemen, please note that they are vital, promising, and useful media for the living systems and nature. I don't think there is any living thing that exists on the earth without the presence of liquid crystal phase in them. It is hardly, therefore, I have my own statement to make as a scientist. It's hardly exaggeration to say that in the chemistry of living system, liquid crystal behavior as important as the carbon-carbon bond. Living things could not have evolved without liquid crystals. That's my statement to make, and I shall demonstrate what I'm speaking. As ladies and gentlemen, all of you know that we are made up of n number of organic molecules. It could be carbohydrates, proteins, peptides, polymer, whatsoever. You take any part of your body, it is made up of organic systems. So carbon-carbon bond plays a very, very important role as far as we living beings are concerned. So these carbon-carbon bonds, or as they appear in the form of different organic systems, it can be it can be carbohydrate, it can be oil, fat, whatsoever. But interestingly, we are made up of, very interesting, we are made up of non-living organic molecules, but we have life. All of you have, I mean, they're all non-living. Organic molecules are non-living, but when they come together and make our body or any living body, life comes out. Okay, here liquid crystal plays an important role. All right. Okay. So I have been telling right from the beginning, life and life, please note very important slide, life and life processes are critically based on liquid crystals. Liquid crystal behavior occurs in DNA, protein, tissue, cell membranes, and so on. And all of you know, our body comprises of 60 to 70% of water. So where this water is, we always talk about water. What is this water? Where it is? Okay. Where this water is? This water, you know that you are made up of n number of cells. Within the cell there is a water. Outside cell there is a water. That's how water is distributed. Now, as far as I'm concerned, I'm quite convinced with the fact that it is, of course, it has a history. There are proofs that everything started with liquid crystals. That is, first liquid crystal was generated in the form of what is known as cell membrane or plasma membrane. Then once cell membrane or plasma membrane is formed, then you have cell components, a cell is formed, then you have tissue, organ, and eventually you get a whole system. Now here I would like to stress upon a point that when you started with the atom, then you go to macromolecule, you started with, one second, I'm sorry. Okay, what is it? Okay, you started with atom. This is very, very important point. That's why I removed that. You start with the atom, then go to molecule, macromolecule, organelle, cell. So here you are, gentlemen. So here you're starting from atom and it's going up to cell membrane. You have component of cell and then cell, tissue, organ, and whole organ system. I would like you to note on the point that everything started with plasma membrane. Plasma membrane is nothing but lyotropic liquid crystals. Here the point is to say that everything started with a liquid crystal. On this earth, life began with lyotropic liquid crystal. Okay, as I said, cell membranes, human have about 100 trillion or 10 to the power of 14 number of cells. Cell size is about 10 microgram, the mass is about 1 nanogram. Cell probably consists of water. Within the cell, there is a water. On the outside, there is a water. Okay. As far as the liquid crystal science and technology or lyotropic liquid crystal science and technology is concerned, it's very clear. The aging is nothing but the continuous loss of water, very systematic loss of water. For instance, when a newborn baby, it has about 78% of water. When it grows old by just 1 year, water drops down by 13%. Means the cell membrane, which is in the form of liquid crystal, now slowly, the lyotropic liquid, this is it's called lyotropic cell membrane is called lyotropic liquid crystal. This lyotropic liquid crystal has a fluidity. Okay, as and when you grow old, because there is a loss of water, this elasticity or fluidity comes down drastically. Okay, it means that the aging is nothing but the continuous loss of water, continuous and systematic loss of water. This cannot be stopped. Once we are born, we are supposed to die. This happens through the loss of water. So there's a loss of water within the cell and outside the cell. Thereby, the liquid crystals, the lyotropic liquid crystals are slowly going towards from, say, fluid state, liquid crystal state to crystalline state. Sorry.
Sir, Yadamagal sir, please unmute yourself, sir.
Oh, yes. Okay, but there's a way. I think all of you know that when you Yeah. Okay. As far as the when you go to a doctor or when you talk to elderly persons or when you meet your teacher, well-wishers, they keep asking you to drink water. What does it mean? It means that whatever loss of water you have as you progress with the age, at least you can keep your cell membrane, allotropic liquids, by drinking good amount of water per day, for 3 to 4 liters of water. You are wetting up your cell membrane, plasma membrane. It remains in a fluid state. So those who have the habit of drinking water, they live long. There are many examples. Those who have the habit of drinking water means that by drinking water, you are trying to wet your cell membrane, plasma membrane, which is in allotropic liquid crystal state. I would give one best example. I try to wind it up with 1 or 2 slides. You take a soap case. You have a soap. Let's say that when you're taking bath every day, your soap is wet and it is quite fluid. It's waxy. But let's say that you go out for 10 days. When you come back, your soap will not be waxy. It will be hard mass. There's a loss of water. It's nothing but allotropic liquid crystal, but it's a hard mass. Therefore, when you wet it, it will come back to liquid crystal state. Same thing happens into our plasma membrane. If you don't drink good amount of water, then there is a problem. You should drink good amount of water in order to keep your plasma membrane in perfect allotropic liquid crystal condition. Okay, these are as far as the fluidity and the behavior of allotropic, means the cell membrane acts as both solids and liquids. For example, division shows you that it's a fluid, and there is a beautiful experiment by one of my close friend. He shows that the cell membrane is as good as a rubber band. See, an erythrocyte red blood cell is grabbed at opposite ends of a pair of parallel particle held in optical traps. You can see the elasticity or the fluidity of your plasma membrane. All right. So I think I should wind up. As far as I'm concerned, today I try to tell you that liquid crystal are the basis of our life. In fact, I'm talking about allotropic liquid crystals. In essence, today I try to tell you that in addition to the different states of matter, liquid, solid, plasma, Bose-Einstein condensate, and so on, there exists another state of matter, liquid crystal. Liquid crystal is something unique because they flow like liquids. At the same time, they exhibit what is known as birefringence. Flow is a property of a liquid. Fluidity or mobility is a property of a liquid. And birefringence is a property of anisotropic crystals. Thank you very much. Thank you, one and all. Thank you very much. I'm open to questions.
Students, do you have any questions? Feel free to ask. You have any clarification regarding liquid crystals? Only thing, sir, we are getting in the chat box. It was a wonderful session. Chat box people are writing about how they liked your session. So I thank Dr. Elamgad for another beautiful lecture. Beautiful lecture on liquid crystals, unique soft matter and fundamental aspects.
Excuse me,
Yes,
ma'am.
yes, ma. You have a question to ask?
Yes, ma'am.
Please go ahead. Go ahead, ma.
Yeah, I can hear you.
Yeah.
Good evening, sir.
Yes, good morning.
Actually, as you have told, that is liquid crystals are exhibiting birefringence properties.
Yes.
And even in our cells also we are having, that is the liquid crystals. So
Yes.
can they are also enabled to exhibit that birefringence property?
Yes, allotropic compared to thermotropic liquid crystals, I think you're talking about birefringence. Yes, allotropic
Yes.
liquid crystals compared to thermotropic liquid crystal, birefringence would be there, but it will be very low. Okay, because there is no organic system. You know what is plasma membrane? Okay, it is a lipid bilayer structure. Okay, there is a birefringence definitely, but compared to thermotropic liquid crystal, it will be less. Thank you.
Oh, thank you, sir.
Questions? Students?
Anything else? I think we should not take Prasad time. We shall discuss
I
later.
have one question, sir.
Sir, there is
Yeah,
one
please.
student, sir. We'll just ask
please,
her
please.
and then.
Sir,
Yes, ma'am,
as
go ahead.
crystal is sensitive to temperature, if I give more heat to liquid crystal, it becomes a liquid.
Yes.
Then if I cool it, it will become a
Liquid crystal.
again liquid, and further it will go to solid, sir.
Yes.
So this thing is also possible.
Yeah, yeah. You see, take a crystal. We make organic molecules. They should be shape anisotropic. We design organic molecules which are shape anisotropic. Either it should be rod-like. I didn't cover that part because of the lack of time. Either it should be rod-like or disc-like. If you heat, to begin with, when we synthesize in the lab, they are crystals. When I heat them, before they go to liquid state, they pass through intermediate state that is known as mesomorphic state or liquid crystalline state. Yes, solid, heat, it will go to liquid crystal state. Further heat, you will go to liquid state. You cool liquid crystal, isotopic liquid, come back to liquid crystal state. Further you cool, it will go to crystalline state.
Okay, sir. Sir, one more doubt, sir. Sir, liquid can be compressed, no, sir?
It can be compressed.
Yeah, in slides you show that liquid cannot be compressed.
To what extent you are talking about?
When you show the differentiation between solid and liquid, you showed no that.
No, this is exercise for you. You write to me to what extent you can compress a liquid.
Okay, sir.
Fine.
Thank you, sir.
What else? I think I should not take much time because
Yes, sir. Yes, sir. Thank you very much, sir, for extremely informative lecture, put so beautifully in the slides and to make students get interested in this new state of matter. Grateful to you, sir, for sparing your valuable time and for initiating the whole process. If it wasn't for you, I don't think we would be sitting here today having this wonderful interaction. And I would request Miss Vidyarani Gurani, who is a 4th semester BSc student of PC Jabin Science College. I request her to give express her opinion about your lecture. Thank you very much, sir.
Good afternoon, everyone. It's my privilege to propose the vote of thanks. I, Vidyarani, the student of PC Jabin Science College, like to thank the organizing team. That is, Royal Society of Chemistry, Local Section Deccan, Center for Nano and Soft Matter Sciences, in association with the KLE Society, PC Jabin Science College, for organizing this seminar. It's my privilege to take the vote of thanks for today's resource person, Dr. C.V. Elmagat sir, who have enlightened us with the knowledge on liquid crystals, the unique soft matter. Your words have sparked the curiosity on us, which will encourage us in our future prospects. Thank you, sir, for enriching our knowledge on soft nanocomposites, various forms of crystals and their applications in various fields, and knowing us about the importance of liquid crystals in life and the various life processes. We are very grateful to you, sir. Thank you so much, sir.
Thank you. Thank you very much.
I would also extend my gratitude to our principal, Dr. L.D. Horkeri, sir, and to the head of the Department Chemistry, Srimati Shashikala Patil, ma'am, for organizing a webinar even amidst the pandemic. I am grateful for the staffs who have worked behind the scene for making this webinar a successful one. Finally, yet importantly, my heartfelt thanks to the participants who made this webinar successful by their active participation. Thank you.
Thank you very much, Vidyarani. Thanks for those well put words about sir. Now we'll move on to the next session by Dr. S. Krishna Prasad. He will be talking on multidimensional technological applications of liquid crystals. Mr. Krishna Prasad is a scientist in Center for Nano and Soft Matter Sciences, Bangalore. Apart from being a scientist, apart from being a scientist with more than 3 century publications and 10 patents, he is also a person who is very much active in outreach activities of the CENS organization, And he's also very much interested in dissemination of science among school children. See, today we realize that our target is these school children who will develop. You, of course, you people are also, you're already interested. That's why you are in BSc. Otherwise, school children are another very important focus area. And Dr. Krishna Prasad has very rightly put his focus on that. I hope we will associate with him further in our activities through our RSC local section Deccan. So now I request Dr. Mahantesh to introduce Dr. Krishna Prasad Garu to the audience so that they understand how fortunate they are to be listening to a person of this caliber.
Thank you,
Over to
Radhika madam.
Dr. Mahantesh.
Thank you, Radhika madam. Good afternoon, everyone. I am Dr. Mantesh M, Assistant Professor of Chemistry, PC Javin Science College, Hubli. As we are in the last technical session of today's online seminar organized by renowned Royal Society of Chemistry in association with CNS Bangalore and our college, PC Javin Science College, Hubli. Really, it is great pleasure to introduce the resource person of present session, Dr. S. Krishna Prasad. Dr. S. Krishna Prasad obtained his PhD in physics of liquid crystals from Raman Research Institute, Bangalore. Subsequently, he was appointed as a scientist first at Raman Research Institute and later at the Center for Liquid Crystals Research, Bangalore, Center for Nano and Soft Matter Sciences, where he is currently working as honorary scientist. He carried out his postdoctoral work at the Technical University of Berlin, Germany, University of Florida, Naval Research Laboratory, Washington, DC. He has been the visiting scientist to Naval Research Laboratory, Washington, DC, Hungarian Academy of Sciences, Budapest, Bulgarian Academy of Sciences, Japan, National Institute of Materials and Chemical Research, Tsukuba, Japan, National Institute of Advanced Industrial Science and Technology, Japan, IT Research Manager, Japan, etc. His research work is focused on several frontline areas of liquid crystalline materials, including their applications. He is a member of the New York Academy of Sciences, Founder Secretary, Indian Liquid Crystal Society, Japan Society for Promotion of Sciences Fellowship, and C.V. Raman Young Scientist Award. He has published more than 310 research publications with H-index 46 and about 10 patents. He is currently an associate editor of Bulletin of Material Sciences. He is active in outreach activities of the Center and Science Dissemination Programs for School Children. With this brief, concise introduction, I am requesting Dr. S. Krishna Prasad sir to start this session. Over to Madam.
Please take over. Dr. S. Krishna Prasad Garu, can you please take over, sir?
Just give me a minute, please. I'll join in a minute.
Come.
Seems to be all right now.
Yes.
I don't know. We came out of the meeting for some reason. So that's okay. Good afternoon.
Good afternoon, sir. Welcome.
Thank you. We lost the connection for some time, so I don't know what stage we are.
Actually, the stage is all yours, sir.
Oh, okay. Then I can start.
Dr. Mahentesh has introduced you, introduced you to all the audiences. So now the stage is yours.
Okay. Thank you. Thank you, ma'am.
Thank you, sir.
In fact, at the outset, it's a pleasure to be part of this workshop. And I sincerely thank RSC, Deccan chapter, all the organizers involved, Dr. Radhika Kanigari, principal of the PC Jabin College, and especially my colleague and friend, Dr. Elamagat, for giving me this opportunity to talk to you on the technological applications of liquid crystals. Before actually I begin my technical talk, I would like to say a couple of things. The first one is actually, today is the day that science has made mankind very proud of something that science can contribute. And at the same time, it's also a day which actually has brought sadness and shame to mankind. I guess that you might have already imagined what I'm talking about. 76 years ago, 6th of August, 1945, science demonstrated how huge energy unleashing can be done at over a very short duration. They demonstrated whatever theoreticians had worked out on their pencil paper kind of thing can actually be implemented on the field. So it's a proud moment for science, but at the same time, it also brought unprecedented level of misery, sorrow to mankind. People suffered a lot of them got killed, people got maimed, and the after effects were there for a number of decades. I'm talking about the atom bomb that was dropped on Hiroshima. So this actually should be a lesson, an eye-opener, even today, even after 75, 76 years, to every student of science, every practitioner of science, that hand in hand, whenever we think about science, whenever we think about technological applications of science, we should always keep the society in mind. We should always keep the negative effects that can come through. And so therefore, we should be beware. We should make sure that the negative effects do not affect us as the atom bomb has done a devastating thing to mankind. So therefore, this is the kind of message that I wanted everyone to remember whenever we talk about technological applications of science. The second point that I want to recall today is something more personal to me and probably has a common feature with Dr. Elamagad also. I guess that he has already mentioned the name. And we are talking about our teacher and guru, Professor Chandrasekhar, who brought us to the field of liquid crystals, taught us liquid crystals, and made us do research on liquid crystals. Today happens to be his birthday, and I do want to dedicate this talk to him. Having said so many things about the aspects that I'm not going to touch upon in the rest of the lecture, let me begin my talk today, which is titled, let me share this. Yeah, I would probably do that, and then yes, but then I will lose if I do that, you know. So therefore, I would probably go here and then start sharing the screen. This is the one. So share. Is the presentation visible?
Yes, sir.
Okay,
Yes, sir. It is visible, sir.
Okay. I don't know why I can't go to the full screen mode. Yes, this is. So that's the title that I have. So the most important aspects are something that my colleague has already touched upon, so-called liquid crystals, which has made my job simpler. So I don't have to be introducing the audience to the field of liquid crystals. But what we are going to talk about are applications and how these inner crystalline materials, so-called liquid crystals, can be employed for a variety, for a plethora of purposes. They can be employed is what I'm trying to convince you with before the end of the talk. So Actually, liquocrystals belong to a much bigger class of materials which are given the name soft matter. These materials actually are the confluence or the meeting point of a number of disciplines of science. Truly being an interdisciplinary science, it combines the concepts coming from physics, from chemistry, from biology, from mathematics, from engineering. A lot of these actually make the liquocrystal science and technology that we know today. So soft matter is an all-encompassing one that also includes liquocrystals. So what do I mean by soft matter? In fact, the kind of materials that we study in undergraduate and postgraduate courses can be referred to in hindsight. Knowing that I have a material called soft matter, I can label those things like metals, typical insulators like, for example, wood, Teflon kind of thing, or semiconductors like germanium and silicon. All those kinds of materials that we are very familiar in our courses, I can label them as hard matter. So why do I differentiate between hard and soft matter? Is because of the kind of energy scales that are involved. Hard matter that we know about the metals or semiconductors, or whatever they are, the structure is held together or the properties combine because of the interactions that are having energy scales comparable to what a covalent bond actually gives us. So that's the kind of energy scale that I already have defined for what are called hard matter. So obviously one should be expecting, without me spelling it out very clearly, that a soft matter, the energy scales must be much smaller. Indeed, it is true. But before looking at the energy scale, let us make a very one-line definition of what soft matter is. And for that, let me say that, let me move this away from the screen. Yeah. So all physico-chemical systems, physical or chemical systems that have large response functions for a small stimulus, they are referred to as soft matter. So I supply very small force or energy to the system, and the system comes back to me with a very large response. Then I could be calling those materials as soft matter. So external stresses, electromagnetic fields, even fluctuations of temperature, they can influence greatly the properties exhibited by the soft matter. As I've already said, covalent interactions are the main binding force in case of hard matter. But as opposed to that, we do not employ covalent interactions in soft material, although the material is still having covalent bonds, but we do not appeal to those interactions, but we look at rather much weaker forces. Like, for example, a hydrogen bond, which is a non-covalent bond, but still the energies are much smaller. These kinds of forces are what we are going to employ in soft materials. One very simple example of that is, for example, a rubber band, which can be easily stretched. Rubber band can be thought about as a spring, where by stretching, actually, you are increasing the displacement between the neighboring regions. But for example, a similar spring can be seen in an automobile, in a car, for example. But that spring needs a much larger force, a much larger energy to be activated. So that's how we compare the energy scales. And for soft matter, the energies can be comparable to kT, where T is the absolute temperature and K is the Boltzmann constant. So this kT value, if we are talking about soft materials, they are very small. For example, consider the kT value at room temperature, which is about 1/40th of an electron volt or 25 milli electron volt. And so therefore, such small energies can act upon soft matter and bring about changes in the structure or change the properties of these materials. So that's why they are referred to as soft matter. I have here put, I don't know why this fellow is not disappearing. I could have shown, I have put some values here, which I wanted to demonstrate to show what the difference in elastic energy between a soft material. Sorry. Yeah, but yeah, okay. Yeah, no, but somewhere there, right? Yeah, it doesn't matter. So the Young's modulus for copper, for example, is a very large value. We are talking about hundreds of gigapascals, whereas rubber, the rubber is only something like 0.01 of gigapascal. So we are talking about 5 orders of magnitude difference in Young's modulus between a so-called hard material and a so-called soft material. So among soft materials, the cousins of liquid crystals are glues, paints, soaps, biological materials, some of which Dr. Yelamagar talked about, colloidal dispersions, polymer melt solutions, a whole lot of them that we combine in our daily life. They all belong to this class of soft material. And liquid crystal is one such material as soft matter, and we are going to discuss the technological applications of these kinds of materials. So let me skip this slide for want of time. The only point that I wanted to show was that the length scales of different materials in the soft matter category can be widely varying. And in liquid crystals, we are talking about something that goes between a few nanometers to about hundreds of nanometers. So that's what liquid crystals get classified and that soft matter category. So I can skip it, except for one thing. I think Dr. Yelamagar didn't mention the connection between liquid crystals and English language, like Shashi Tharoor, for example. He would have pointed out that liquid crystals, the phrase is an oxymoron. An oxymoron is a combination of two words which have opposite meaning. So let me take a few examples here. An open secret. Secret is no more a secret if it is open. A tragic comedy, if it's a comedy, there can be no tragic ending. Funny, seriously funny, if it is serious, then it's not funny. So such things we can always talk about, and typically we say it's an original copy, original copy. So such things, for example, are called as oxymoron. And so liquid crystal, the phrase appears to be an oxymoron. We are talking about something which is a liquid and something which is a crystal. And our common experience is that liquids flow, as I think Dr. Yelamagar was also mentioning, whereas crystals do not flow. So if you are trying to combine these two materials and come up with a new structure, come up with a new state of matter, you have got something, a liquid crystal. And I think he has already convinced you that liquid crystals is a new state of matter, is a different state of matter, is neither a liquid nor a crystal, but combines some of the properties of these two and brings about new structures, new properties into the medium. So that's what liquid crystals are. But the rest of the kind of introduction that he has already given, let me skip all these things. And my talk actually is going to stress upon, I don't know whether the, it will give me, oh, sorry. Okay, doesn't matter. I was looking for a pointer that doesn't seem to be coming through. I think I don't see it here in Zoom. I'm not sure. Yeah, forget it. So I'm going to concentrate on this particular class of materials, the so-called liquid crystals, and I have shown here the simplest of them, which I think he introduced already, the so-called nematic liquid crystal, which is essentially a liquid. It is no different from a standard liquid, like, for example, water or petrol or any such liquid, except that the molecules are no more globular, no more spherical, but rather are elongated along one direction, which make them look like cylinders. And so therefore the cylinders are more or less oriented along one direction. So therefore they have something called an orientational order, but they do not possess so-called positional order like in a solid. And that's what makes them special compared to either solid or the liquid. So the liquid crystal, the orientational order that he has already talked about, let me borrow that concept and continue from there, looking at different concepts. So I'm going to mainly stress upon the thermotropic, the temperature-driven liquid crystal materials, and maybe touch upon at the end, at the lyotropic. He talked about the biological aspects, how lyotropic liquid crystals are essential for formation of membranes and life itself. So that's something, maybe one topic, one little topic that I'm going to touch upon towards the end on lyotropic liquid crystals. Yeah, no, my phone. I'm sorry. So the properties that I want to borrow, are like we talked about the shape of the material, which is anisotropic, and I think he has already introduced what is anisotropy. Isotropy is the phenomena wherein the property remains the same irrespective of the direction along which I am looking. For example, a cylinder is an anisotropic object, whereas a sphere or a ball is isotropic. The diameter of the ball remains the same irrespective of the direction along which I am measuring the diameter. But the size is no more isotropic for a cylinder because the height or the length of the cylinder is different from its diameter. So therefore, similarly, like what we talk about for the shape, we can also talk about properties which are anisotropic. And here is one that I'm talking about, so-called optical anisotropy, or a phrase that we already talked about, so-called birefringence, which means that the refractive index has different values along different directions. So we define something called delta n, which we call as the birefringence, or the so-called value of the double refractive index, which is given by the difference, the numerical difference between the extraordinary refractive index of light and the ordinary refractive index of light. I don't have much time to talk about the optical details of it, but please trust me and believe me that this birefringence property can be very clearly defined for any material which is optically anisotropic. It need not be a liquocrystal. I think he talked about cellophane tape as an example, perhaps he talked about it. A cellophane tape is a very good example of a solid exhibiting birefringence. He also talked about stress-induced birefringence. I think he was talking about a ruler, a scale, a plastic scale, for example. When it is stretched or when it is stressed, then it exhibits birefringence. So optical anisotropy is one property that we are going to employ in this in the applications that I'm talking about. And similarly, the dielectric constant, I think you've already been introduced to dielectric constants. For example, all insulating materials, whether it's wood, plastic, Teflon, for example, they all have their electric properties decided by a property called dielectric constant. And this dielectric constant again is anisotropic in case of liquocrystals. Like what I did for the birefringence, I can define the dielectric anisotropy, which we call as delta epsilon, is given by the difference between the dielectric constant parallel to the axis of the molecules which form the liquocrystals or the so-called cylinders. And the difference is taken between that value and the dielectric constant perpendicular to the long axis of the cylinder or along the diameter of the cylinder. The difference between the two gives me the dielectric anisotropy. And then we are going to look at the elastic properties, which are also important. I have here put something that probably I would not be discussing in detail for this audience, for this talk, something wherein we can deform liquocrystals in different ways, elastically deform them. So therefore, that's what I'm trying to do here. I can shear them in different ways, and these shear behavior is actually governed by different elastic constants. The same way that I talked about Young's modulus for either rubber or copper, I can talk about the elastic behavior using these three terms called the so-called splay or the twist or a bend elasticity of liquocrystals, and then I can describe what should be happening to these materials when they have undergone such deformations. I'm sorry, this is bothering me a lot, but I have to live with it, I guess. So, having defined all these fundamentals for these things, let's start looking at applications. And one of the most important applications that liquocrystals have become famous for, in fact, the younger generation should be thankful to liquocrystals every single day of their life, because without which life is now cannot be imagined. Even we cannot imagine our life now without mobile phones. And I think especially the younger generation, I can mention that Facebook, WhatsApp, Instagram, Telegram, or whatever kind of social media that you are on, and then keep loading information or downloading information from that, would not have been possible if liquocrystal displays were not possible at all. So it is the liquocrystal display that actually is the paramount importance of applications of liquocrystals that we today have come to enjoy the outcome of liquocrystals being anisotropic liquids. So among applications, I'm going to first talk about the display applications, and the display need not be just a mobile display. It can be like what you have, a laptop or a computer monitor that you have perhaps using a liquocrystal at home, for example. Unless you have a huge, very heavy television at home, what you have today, if you have bought it in the recent times, it would certainly be a liquocrystal television that you have, or a so-called LCTV that you would be having. In fact, even the projector that probably is used if you are sitting in a lecture hall is also using a liquocrystal to project information onto a screen. So there are different kinds of liquocrystal. D stands for display. Liquocrystal displays that are possible. liquid-crystal display is what I have abbreviated as LCD. And they come in different flavors, different varieties. But the most common of them is the so-called twisted pneumatic liquid-crystal display, which is what I'm going to discuss in somewhat detail. And then I touch upon something, that's why I have slightly graded the topic in plane switching. And then there are other varieties which are more important, but more detailed. So therefore, this talk, I'm not going to touch upon the so-called ferroelectric and aferroelectric liquid crystal devices. I'm not going to touch upon. So we are going to concentrate mostly on the so-called twisted pneumatic liquid crystal display. So let's see what it means and how it works and how it has made the displays on our mobile screens possible. The principle involved in an LCD or a liquid crystal device is a very simple one. And to appreciate it, what I have done here is I have taken a matrix of 5 by 7, 5 columns, 7 rows of something which can be taken to be a light bulb. That's why I have put them as bright spots. Okay. So we have about 35 bulbs or 35 spots here. So on the left, you see that all of them are lighted up. So therefore, you have 35 bright picture elements. Or when you buy, for example, a mobile, you would come to know that how many megapixels of the camera that you are going to buy, how many megapixels of the display device that you are going to have. We call them as HD screens, FHD screens. They're all decided by the number of picture elements or the number of bulbs that can be independently lit up, independently can come on or off in a display device. So therefore, understanding this matrix principle lies at the basis of making a display device. So what I have here is all the 35 bulbs, all the 35 bright spots lit up. But on the right, you see that I have made some of them switched off. Those are appearing in gray now, but some of them are still appearing bright. Okay, so selectively, I have turned off some of them. But by doing so, without doing anything, I have only selectively put the switch off for some of them, and it makes me think that there is a pattern that is being displayed. I can imagine the gray spots to be giving me the pattern, and I can imagine that this is representing the English alphabet T, right? So what I have done here is I took a matrix of bulbs or bright spots and then selectively turned some of them off. By doing so, what I have done is I have created a pattern already. I have already created information that can be displayed by simply turning on or off some of the switches. Okay, this is the basic principle that you can do that even with pencil paper. For example, take a set of open circles and then fill them up with pencil with a pen or ink or whatever that you have, and then you can create a pattern, right? So Chukki Ata Artha Idvi Navala, for example, when we were young, and so therefore the only thing that we need to do is we used to have empty squares and we used to put crosses in them, and there used to be a pattern already, right? The same thing actually comes here also. We can make patterns, we can transfer information by selectively turning the switches on or off in this matrix. Okay, so what do I do? I have already this basic principle. Selectively, if I turn the pixels or the picture elements or the bright spots or the bulbs, selectively turning them on or off, I can create information. So what do I do? If I do it manually, for example, I can still transfer information, but this is not a very effective, this is not a very convenient way or a very elegant way of somebody is trying to draw on my screen. May I know what the purpose is? Hello?
Sir, I will delete, sir. I will delete those here.
Okay, I don't know what the purpose is.
Okay.
Okay. Okay. So I need to have some of these properties satisfied before I can employ liquid crystals for display devices. The first one is light can be polarized. This is something that Dr. Elamaga spent significant amount of time to say how light is polarized and what is meant by crossed polarizers, parallel polarizers. What happens to the light that is trying to pass through a set of parallel polarizers, it will come through, whereas a set of crossed polarizers whose pass axis is perpendicular to each other, light gets blocked. That's what he very well demonstrated. So this is one property that we require to make the devices possible. The second one is the light liquid crystals can make the polarized light pass through them in a certain fashion. They can change the direction of polarization when they pass through the liquid crystal device. This is another property that we will be banking on, that we will be ensuring exists. The orientation of liquid crystals can be changed by applying an electric field. I don't think that Yelamaga talked about it. We already talked about a property called dielectric anisotropy. When I apply to a liquid crystal film, when I apply an electric field, I will be appealing to this so-called dielectric anisotropy. And so therefore, the applied field will combine with the dielectric anisotropy of the material. By doing so, it applies a torque to the molecules and can change the direction of orientation from one to another. And this is the third property that we would be requiring. The last one is actually, I have to enclose, I have to confine, I have to contain this liquid crystal between transparent substances, because I want a display device, which is an optical device. So I want the light to come through or get blocked in a certain way. So I need substances or substrates or sheets which are transparent to light. I need to have that to confine the liquid crystals. I take two sheets and then put the liquid crystal behind them, between them. And so therefore I have confined the liquid crystal between the transparent states. But as I said earlier, I also want to apply the electric field. So I want special kind of transparent sheets, which are not only transparent optically, but they should be able to apply an electric field to the material that is contained in between. So I can't be using a metal sheet, for example. A metal is, of course, can apply electricity, but then it is not transparent. So there are special semiconducting substrates which are available, semiconductor coatings available. We put them on glass. These are called, typically indium tin oxide is a material that is used. It is transparent as well as it can conduct electricity. So we need to have substrates, we need to have sheets which can contain the liquid crystal, but at the same time satisfy the conditions of being transparent and apply electricity also. So once we have satisfied all these things, we can create a device. Probably I'll skip these introductory things which Elamanga has already talked about. What we are going to do is confine the liquid crystal in such a way, like I have shown in this cartoon. What I have here is one substrate, and wherein you see something like a corrugated ruling, which actually makes the liquid crystal get in between those rulings. And so therefore, liquid crystals get oriented along that particular direction, along this plate. There is another plate at the bottom. Let's call this as the top plate and the other as the bottom plate. And on the bottom plate, the liquid crystalline molecules are oriented in a direction which is perpendicular to the top plate. So what you have is a twisting of the liquid crystalline orientation. As I go from the bottom one, the orientation of the liquid crystal is like this. When I go to the top one, it is perpendicular, orthogonal to the original one. So therefore, since these materials are elastically soft, as I already told you, that they belong to the category of soft materials, the elasticity associated is very small. So therefore, the liquid crystals being soft, they conform to the kind of orthogonal orientation that I have on the two substrates and undergo a twist on going from one plate to the other. So I have called these kinds of substrate, these kinds of displays as a twisted nematic. Since nematic is the liquid crystal that I'm employing, these are twisted nematic displays that I have here. So please remember, once I have such a twisting configuration, if I am, I'm sorry, if I am putting a plain polarized light to go through that kind of a cell, then the polarized light direction also gets twisted. Sorry. As it passes through the device. So that's what I have shown here, a white band. This is the polarized light. It undergoes a twisting and comes out as a bright piece of light passing through the device. So this is my so-called equilibrium or no electric field applied state. So please remember, I have a twisting configuration of the liquid crystal. I have a polarized light that actually undergoes a twist of its orientation direction. The polarization direction actually undergoes a twist. and it comes out as a bright beam of light. Now, that's what I have sketched here again in this cartoon. This is the so-called bright state. Now, what do? I apply an electric field. I've already told you, when I apply an electric field, the dielectric anisotropic gets coupled to the applied electric field. There is a torque applied. The molecules which are actually lying in the plane now want to go along the electric field direction. It's as if the electric field pulls up these molecules to stand up and to be parallel to the direction of the applied electric field itself. So therefore, instead of lying down in the plane of the substrates now, the molecules are standing perpendicular to those substrates. So if they stand perpendicular, then actually what you will be seeing is the ordinary refractive index of light. And so therefore, between crossed polarizers, there is going to be a cancellation of light. The light cannot pass through the device. So in the first one, when the electric field was not there, the light beam passes through it. So therefore, the device appears bright. And in the second state, when the electric field is applied, the light beam gets blocked. And so therefore, the device appears dark. And from our simple kind of matrix arrangement of bulbs, we know that if we can selectively put the pixel or the device on or off, we can create patterns. And that's what I have done here in of examples that I have put here. For example, look at this display of what appears to be the numbers 3 and 3 or 33. This is simply now, I have got, if you look at the top, for example, 1, 2, 3, 4, 5, 6, and 7. I have 7 segments here, 7 twisted pneumatic segments here. And each segment I can selectively turn on or off. And that's what I have done in displaying this number 33. I have kept these one, the top one and this one, the left pixels, left segments to be kept bright, and the rest of them I have put the electric field. So what you have are 5 segments which appear dark, 2 of them bright, and so therefore it will give you the impression that I'm trying to transfer information of 2 numerals being displayed, the numbers 33 being displayed. This is how simply the leucocrystal display works. So selectively turning some of the picture elements on or off is all the principle that drives that beautiful leucocrystal device that you are holding in your hands when you are using a mobile phone. So this is what in detail I am showing here. Each of the segments I have shown, and I have made an independent electrical connection. I have to have switches, right? As I have mentioned. So I have to selectively turn them on or off. And so therefore, I have got electrical connections to each of the segments for this so-called 7-segment display. So each of the number that I want to describe or display, I need 7 segments. So I need at least 7 electrical leads coming out of such a display. But for each numeral, I have 7 connections. So as I increase the number of segments, as I increase the number of numbers that I want to display, I'm going to increase the number of electrical connections. It is okay if you are talking about a calculated display. A calculated display is also a leucocrystal display. And so therefore, for that, you are going to display only numbers. And so therefore, the total number of connections that I have are still manageable. They are not very high, very huge kind of number. But in a mobile, you are not just looking at numbers. You are not just looking at alphabets. You are looking at a graphic information, right? A graphic information. For example, I have made a very simple graphic information. I have put an emoji here. And for that emoji, I have to have number of matrix elements to display an emoji, unlike the display of numbers or alphabets. And so therefore, if I'm talking about a matrix display like that, and I consider, for example, a very low grade display, which is called a VGA display, has only 640 by 480 elements. Imagine the kind of mobiles that you buy today. They are FHD kind of device, full contrast displays that high, and so therefore the device. But even for this simple VGA kind of display, I already have 640 by 480, which is something like 300,000 electrical links that are drivers or switches that are needed to operate such a device. I'm talking about a monochrome, a black and white kind of display. None of us like a black and white display. We want color. And for color, each picture element, technology drives it that way. Each picture element has to have at least 3 pixels, the so-called red, green, and the blue, so-called primary colors, make them up. And so therefore, I need to be multiplying this 300,000 by a factor of 3. So even for a simple VGA display of a 640 by 480 pixels, I already need something like 1 million switches to be operated. Tell any electronic engineer to give you a circuit which can drive 1 million switches at a very short time. Please remember, we are talking about video in a mobile. And so therefore, you're already talking about 16 frames per second. So you have only about 50 milliseconds or so to operate this 1 million switches. And so therefore, it becomes an extremely cumbersome kind of electronics that you have. So people have done a variety of improvements, variety of technological innovations have been done to bring about the kind of devices that we have, which are having still manageable kind of electronics. If I don't have time to discuss in detail all those kinds of details, but I'm only showing some of these pictures just to show the kind of complexity involved in creating the kind of display device that you use when you use a mobile phone. So with some of these things called matrix addressing phenomena, etc., instead of having M into N, we made 640 by 480. That's what I mean by M into N drivers. People have come up with beautiful protocols which reduce the number of drivers to M plus N. So instead of having 1 million, you have only 1,000 switches to be operated, which makes life much more simple. And that's how this so-called matrix addressing or multiplexing of the devices has happened. It also brought in problems in the field, and I'm just going to show the kind of problems. For example, if you don't spend much money to buy the kind of display device, here is a laptop. Somebody has bought it without paying much money. And so therefore, everything costs money in life, right? So a good device means you need to pay more. So whereas here, what we are seeing is this device is not so good. And so therefore, what you see is a problem already. What I have done is I have tilted this device to different angles, and I'm trying to see the same picture from different angles. And you also already see that the coloration is already bad here. But for example, for this tilting of the thing, you already see very bad contrast. And look at this tilting. It's a horrible device. You see it as if it's a negative of a film. Okay. So therefore, what appears bright appears dark, and vice versa, with giving you a negative contrast. And so this is a serious problem that display device people had to address. And so therefore, a variety of innovations have been done over the past 30 or so years. Each of them a beautiful one. Each of them got a patent. Each of them employed by the industry to improve upon the display device. For example, if you wanted to buy a device 3 years ago from Amazon, the same thing would have cost you thrice the money, whereas this year it came down because of these innovations. So therefore, this industry has transformed itself extremely, extraordinarily well in the past 10 years or so, and has given us beautiful devices to employ. Probably it's the same thing, but I'm going to not talk about. One of the benefits of that has made a good device is the so-called thin film transistor. This is like making transistors which are deposited on glass. That's not an easy technology that we are talking about. Putting transistors, something like 1 million transistors on glass is a very difficult proposition that we are talking about. And these are very sophisticated technologies which have made the kind of devices that we are talking about. So I won't spend much time on those things. I just want to touch upon one aspect to say that the device that you are using today does not actually employ, if you have bought it recently, does not employ the so-called twisted pneumatic, but it actually employs IPS technology. If you happen to browse through the specifications of the device, you will see that the display is actually an IPS technology, they say. IPS stands for in-plane switching. It avoided some of the serious optical problems that the standard twisted pneumatic device had, and it has made life much better. And there is a comparison here between the standard what existed before the IPS technology and what is now available with the IPS technology. So it reduces the problem that was coming from the blackening effect. Wide viewing angle is possible. Some problem that I already showed you of how the display looks different from different angles. For example, with the IPS, that problem doesn't exist. You can view it over very wide angles. It may be not a blessing. It may be not a good feature. If you're trying to view something on your mobile and your mother passes by, you don't want her to see what you are viewing on the display. But generally, it is not so. You want others also to be seeing on a television. For example, a family wants to sit around and watch a nice movie. So, for example, for such issues, you want a wide viewing angle kind of devices. So, therefore, it's a very nice improvement over the existing technology that we have, the so-called IPS, or the in-plane switching technology. I'm going to switch gears and now go to a non-display application of liquid crystals. The display applications of liquid crystals have achieved a certain maturity already, and so therefore newer and newer applications for liquid crystals are being talked about, and this is something that I am touching upon in the next few slides. And this is something wherein I have called them as dimmable windows in airlines. If you have happened to travel by Boeing 787, so-called Dreamliner, you would have experienced this. This is the one shown on the left is actually a standard kind of window, wherein if you are traveling by, if you are sitting next to the window and there is too much sunlight, what you want to do is put the shutter down. But by doing so, what you have done is you will not be able to see outside, and you will not be able to enjoy the view that the mountains or the rivers over which the aircraft is flying. You will not be able to see them. This is disturbing me too much. I don't know who is doing this art on my screen. Please stop this. It appears to be Mr. Praveen. Please stop drawing on my screen.
Mr. Praveen, you will be removed from the group.
Yeah.
Please continue, sir. I'm sorry for this disturbance.
No, but I don't know what's the necessity.
I know, sir.
If you don't want to be part of the workshop, it's better you log out. Okay, let's not get distracted by that kind of a thing. So here is a newer kind of technology that is put into such windows. And for demonstration, what has been shown is the same window put in 3 different states. For example, on the rightmost, you see that the maximum amount of light is let in, and in the middle, the least amount of light is let in, and in the left extreme, I have some part of light let in, and therefore it appears gray. So therefore, now I can control. It's as if these 3 windows have different amounts of light coming, but that is not true. The same window can operate in these 3 states. That's what the demonstration is about. And so therefore, there is a switch provided underneath. By putting the switch in different positions, I can control the amount of light that comes through. This is what is meant by dimmable window. So this is convenient for a passenger. What they have done is they have put an electrified gel that can take an electric field and change its state. And so therefore, when the electric current increases, the gel gets darkened, and so therefore it reduces the amount of light coming in. So if you put the electric field off, the gel becomes lighter, and so therefore allows light to come through. So therefore, by applying an electric field and appealing to the special kind of gel that is possible, one can control the amount of light. But the problem is, whatever the technology that has been employed in these Dreamliner aircrafts, or the so-called Boeing 787, this is a very slow technology. In fact, it takes a minute or 2 in order to change its state from either allowing all light or getting transparent, partly transparent, or completely blocking the amount of light. So it takes a lot of time. And so therefore, this technology is okay for an aircraft. But if you want to employ it elsewhere, the kind of application that I'm going to show soon, this is not a very attractive technology. This is where the liquid crystals again have come to our rescue and have demonstrated it is possible to create such a dimmable window by using leucocrystal and appealing again to the kind of anisotropic properties that I talked about, that they have two refractive indices. I already introduced earlier that there is the birefringence is defined by an extraordinary refractive index of light and an ordinary refractive index of light. And here is such a gadget, here is such a device that appeals to the presence of two different refractive indices. What I have done here is, which we call as actually, this is an innovation that is done at our center. This is something which we call as, technically we call it as an electrically switchable transparency, but for a popular thing, I call it as fog on demand. What is fog? Fog is nothing but presence of two different materials, water droplets, present in air. So if you go out on a winter morning, there is fog. This is because overnight, water droplets would have condensed into the air around us. Because of this condensation, you have two materials. Of course, the size of the droplets is important. You have two different materials, water, which has its refractive index as 1.3, and air, whose refractive index is 1. So you have two materials whose refractive indices are different. Both are transparent, but their refractive indices are different. So this coexistence of materials having two different refractive indices is what is important for the creation of fog. Okay, so that's why as sun rises, as the atmosphere gets heated up, water droplets get evaporated, and it becomes only a single material, only air is left over. And so therefore only one refractive index, it becomes transparent. So fog has lifted and it becomes transparent. So you can create a similar fog or no fog kind of thing using a leucocrystal material and create very fast switching dimmable windows. And here is the technology. What I have done here is, again, two plates which are transparent and electrically conducting. We are familiar with that now, right? So now what I have done is I have taken two different materials. One is actually a polymer. That polymer has one refractive index, which is labeled as N sub P. Polymer refractive index is N sub P. And the leucocrystal, as we already know, has two refractive indices, N sub E, or extraordinary refractive index of light, and N sub O, the ordinary refractive index of light. So I have enclosed the leucocrystals as droplets in the polymer. There is a lot of technology that is involved. I am not discussing those things. You have to embed droplets like water droplets getting embedded in air. I have to technically, physically embed these kinds of leucocrystal droplets inside a polymer sheet. If I do that, so now when light actually impinges on such a device, when it sees a leucocrystal molecule, it can see either an NO or an Ne. In this kind of state, it sees both NO or the Ne. The polymer has a diffractive index N sub P. The design is such that it satisfies this condition that I have shown here. N sub P is equal to N sub O, the ordinary refractive index of the leucocrystal, but it is not equal. By leucocrystal definition, N sub O is not equal to Ne. Delta N has to be finite, right? Not zero. So therefore, NP is not equal to Ne. So wherever the light sees the polymer refractive index as well as the extraordinary refractive index of light, it gets scattered. Same way, light gets scattered when there are water droplets as well as air. So this panel appears foggy. It scatters light, so therefore it appears foggy. So now I apply an electric field. As we already know, apply an electric field, the leucocrystal molecules want to be pointing along the electric field direction because of the torque that I mentioned earlier. And so therefore, the light now sees the polymer refractive index. It also sees the ordinary refractive index of the leucocrystal. And because of this condition, NP is equal to N naught, it behaves as if as if there is only one refractive index that it is passing through. So therefore, it becomes transparent kind of device. So without the electric field, it's a scattering state. With the electric field, it's a transparent state. So you can switch between the scattering and the transparent state. You can switch between the fog and the no fog conditions by applying an electric field. And that's what we appeal to create panels like this, for example. This is such a panel that has been created at our center. And here it appears like a blank panel. There is nothing interesting in this. What I have done is I have kept something behind this device, and light is impinging on this panel, but light is not allowed to go through this because it gets scattered. So therefore, I do not see what has been kept behind this panel. Power is off now. So now I turn the power on. You see, I had displayed the simple piece of information kept behind the panel. There is a printed sheet which is behind this panel, and it has this information that is being seen now because the power is on. I switch the power off, it goes to the scattering state. I turn the power on, it becomes a transparent state. So this is a dimmable window, which is at the flick of a button, but I can do it extremely rapidly in millisecond kinds of time scales. I can flip this between these two kinds of things. So therefore, people are now coming with very novel applications employing such fog on demand kind of panels. For example, here is a huge office room, and here is where the boss sits, for example. And there is an industry leader who has come and wants to have a closed room discussion with the boss. There are also other people here who are working on different things, and the boss doesn't want them to be a party to the discussion that is being held between these two people. So what does the person do? The person actually flips a button, and you see now the other side is not seen at all. In the bottom panel, you do not see this discussion or where the other employees of the place are working. You do not see them at all. It becomes a scattering state. So in the so-called transparent state, everything is seen here, including the window or the scene outside the window. But at the flick of a button, that is blocked completely. It goes to a scattering state and provides you the kind of privacy that people would require for such kinds of operations. But this is not simply something wherein you want to create privacy, or you want to use it as instead of a blind that is put on the thing, or a screen that is going to be put on a window to block the amount of light. It has far better uses than that, because it can now enter into controlling the room temperature, controlling the amount of sunlight that comes into our rooms, and to heat it up, especially during summer when the sun is very harsh. The entry of sunlight into the room is what actually heats up the room because of the near infrared beam that is contained in the solar light. The infrared beam heats up the room. And so therefore, if you can selectively block that using these kinds of panels, if you can selectively block the near infrared, then you can keep the room cool even without appealing to air conditions, or at least even if you have an air condition, the load on the air conditioner is going to be significantly reduced, and there is going to be a significant energy saving that happens because of these kinds of panels. And in addition, of course, especially when there is a harsh sun, there is also a lot of UV that comes through that can be reduced by special kind of panels, wherein we are going to put UV blockers, which are going to block only the UV, but not the visible light. The visible light still comes through, but blocks the UV. So selective flipping, selective wavelength flipping can be conveniently done using those panels. I won't go into the rest of the kind of thing. Ma'am, how much time do you have? Can I take 10 more minutes?
Yes, sir. You can take 10 minutes, sir.
10 minutes, certainly. I will try to complete it within that. I'll rush through some of these things. I wanted to show this because we all enjoy something that is colorful. And the color abounds around us. Nature is full of color. We enjoy, we appreciate nature because it's colorful. Okay? But we also enjoy color made by man. And on the left, I have shown here a store, a shop that sells colors. And especially during Holi, we all appreciate this very much. We combine these colors and play with it and enjoy the Holi day, right? So these are actually the color in these kinds of materials are coming from what are called pigments, okay? It is the pigment which selectively absorbs certain wavelength of light and gives you the impression that it has a certain color. Okay, impression is because the color actually is an imagination of the brain. Actually, it's just certain colors are absent or present. Brain thinks that they have a certain color. Okay, so therefore, these pigments are the ones that we get introduced to color very easily. The problem is when you are using pigments, it is like a person who creates textile colors uses pigments. But one of the serious problems with pigment coloring is that they fade. What you bought as a bright yellow shirt or a bright pink sari last year has already got faded because you wore it several times and it was exposed to sunlight. And so therefore it gets faded up. But nature or the color in nature, or for example, the color of the bird or a peacock feather don't fade at all. Okay, this is because the way color is done is not because of pigmentation, is not because nature has added a particular dye that it becomes colored in a certain way, a blue or a black or an iridescent green, is not because of a kind of color that exists, but because of the structure. You would have heard lectures yesterday about nanostructures in materials. This actually appeals to nanostructures and creates a new field of science called photonics. And the entire field of photonics appeals to how to create color, how to play with color using nanostructures. And here, I have shown here the same feather of the bird. If you look at under an electron microscope, you see nanostructures. You have pores, you have holes of a certain wavelength. And that is important. The diameter of the hole having a particular size actually gives you a particular color. And the advantage is they're angle dependent. You take a peacock feather and you look at it from an angle, it looks it gives you a different color. Whereas if you were to be looking at keeping it normal to your eye, it gives you a different color. So the color is angle dependent, and the peacock feather never fades. The feather of a bird, the color of the bird is never changed day in and day out. It gives you a wider variety compared to the man-made colors of the pigmentation. And most importantly, it is never gaudy. By gaudy, I mean, if you keep looking at the pigmentation colors, your eyes get strained. This doesn't happen with the color that comes from nature. Your eyes are never strained by looking at the beautiful color around us in the natural form. So therefore, structural colors are what are important if you are talking about nanostructures and tying it up with color. This comes because of a property called chirality. And by chirality, what I mean is handedness. And by handedness, I mean your left hand, left palm, for example, is different from the right palm, right? Different in the sense that if you put your right palm in front of the mirror, the image seen in the mirror appears as if it is the left palm. This is something that we are all very familiar with. And early on in our life, we got amazed by this, of how we look like our own mirror images. And this is true not only of objects like the hand or the palm, but also in the molecular world. This is an anisotropic carbon, for example, or an atom which is tied to 4 different atoms of different varieties, and this gives it an anisotropic or a chiral form. But it is not restricted to just molecules, it goes all the way up. A DNA is a chiral structure. You see the twisting happens in only a certain way for the kind of base pairs that you have. And it's a double helix. So therefore, the helix of a particular combination is opposite to that of the opposite pairs of the base. So therefore, this double helix is another manifestation of the chirality or the handedness of the molecules. You can see structures which are made like that. And biological organisms also have chirality or handedness. Here is a picture of a snail, which is both left spiral as well as right spirals that you can see in organisms. You can also see, for example, spiral staircases. They are chiral, they are helical. And Indians, they are marvelous, really, creating all kinds of things which they can see in nature. Here is something that we would probably be, not only probably, I think we call them as Edamuri Ganesha and Balamuri Ganesha. It suddenly Hegirutto adar mele we call it Edamuri or Balamuri. In fact, these Ganeshas are chiral Ganeshas now. you see that the left one is the mirror image of the right Ganesha. So next time you go to a Balamuri Ganesha, you observe how the Sondilu is done compared to a Edamuri Ganesha, which is more often seen than the Balamuri one. So imagine a chiral Ganesha next time you visit a Ganapati temple. Okay, so these are also chiral structures. So handedness exists in either the molecular form or in the kind of structures that we are creating, employing these kinds of chiral structures. Liquid crystals can also be made into chiral structures. And the beautiful thing about it is the same kind of helix that I showed in the DNA organization can be done in liquid crystalline kind of materials. And now the so-called pitch of the helix can be fine-tuned, and you can make it comparable to the wavelength of light. And when that happens, there is going to be a selective reflection of light, which means that only certain wavelengths of light are reflected from the material and others are transmitted. What do I mean by that? I mean, when you look at the ordinary mirror that you are familiar with, the entire Vibgyor is actually mirror reflected from the mirror that we employ. All the 7 colors that we are familiar with, the violet, indigo kind of thing, all the way up to red, each of the colors is reflected by the ordinary mirror that we know. So therefore, the mirror serves the usual purpose of everything is, every color is reflected from the thing. And so therefore we appear very normal. But now we have chiral liquid crystals, which are selective mirrors. That means only a particular color is reflected. So therefore, if you are sending a white light and getting it reflected from the thing, whatever you have, whatever you are trying to view, only the blue component, for example, is seen in the mirror, and the rest of the components are sent through. So even though the object has already all the 7 colors, the mirror image will have only 1 color, and the rest of it are transmitted. So this looks just of a scientific curiosity. It is not. Beautiful applications have come up. And one of them I want to touch upon is the very simple thing: detection of skin temperature. Something that we are very familiar is fever thermometer. So you use a thermometer to check the temperature. But imagine you are having a little kid at home, a nephew or a niece or a cousin, or whoever it is, a 1.5-year-old child. It has the tendency of biting everything that is put into its mouth. And so therefore, definitely you don't want to put a mercury thermometer into the mouth of the child. So checking fever temperatures are somewhat difficult in children of that age. So instead of appealing to a mercury bead thermometer, can you use a thermometer which tells the temperature in terms of temperature? So appeal to the selective reflection that I already talked about. And yes, it can be done. So therefore, here is a piece of such a material which is stuck on the forehead of the child, and you see it exhibits different colors. So now the color and the temperature are correlated very well. There is a lookup chart. If it is 37 degrees, it's violet. If it is 38, it is green. If it is 39, I'm talking about Celsius, or if you are talking about 98 degrees, which is slightly feverish, it is blue. If it is 100 degrees, alarming already, it is green. If it is 102 degrees, a viral fever kind of condition, the film actually turns yellow. So already alarming you that the child is having a viral fever or a significantly high temperature. So just by looking at the color, it's a strip that has been put on the forehead, and just by looking at the color, you can make out the temperature of the underlying surface of the skin. So therefore, they are very nice kind of skin contact thermometers that are now commercially available, and soon probably they will replace all the mercury bead thermometers that are available in the market, and very effective, very safe, and non-intruding into the body. They are just put on the forehead, for example, and the healthcare person, even from a distance, can make out what is the temperature instead of coming close to the person and then trying to take a readout. But they also have other kinds of very simple commercial applications, like a mood ring. I already told you that the temperature and the color correlation exists between these kinds of systems. And so therefore, if you are wearing such a ring on your finger, a cholestric or a chiral or a liquid crystal that has a chiral character, if the ring is made of such a material, the mood of the person, because when we get angry, for example, the temperature of the underlying surface increases, and when we are happy, when we are cool, actually, the temperature varies slightly. And so therefore, these mood rings can be fine-tuned to such body temperature variations. And even from a distance, you can see that this is blue, so therefore the person is cool. If it becomes red, you know the person is very unhappy or angry. So the next time you want to gift someone on a Valentine's Day, think about gifting this. So you can easily judge even from a distance whether the person is angry about you or happy about you. These are not just esoteric applications, such simple, mundane kind of applications, but they're also used for tumor mapping. The same kind of situation that I mentioned earlier, the skin temperature can be easily mapped by the surgeon who is going to perform the operation to remove a tumor, because tumor is a region which has a slightly higher temperature compared to the surrounding. So therefore, they can be easily mapped. And even before operating, the surgeon can make out the extent of the tumor. For example, there are blue regions here compared to the rest of the yellow or red kind of regions. These blue regions are where the tumors have developed. And so therefore, the surgeon knows that the topology, what is the area and the topology of the tumor before even opening up for surgery. And so therefore, proper preparations can be done to do a proper surgery to remove such tumors. In fact, beautiful technological applications have come up with such chiral leucocrystals. Unfortunately, I don't have time to discuss those things. There are distributed feedback lasers that are possible. You can take a polymer sheet and enclose such a leucocrystal in that, and then come up with a laser on a film. On a film, you have a laser coming in representing all the three primary colors, the red, the green, the blue laser. All are created on a single sheet of material, a polymer material in which such a chiral leucocrystal exists. And the thickness of this laser is only a couple of mm that you have. Couple of millimeters, you have a beautiful laser that can cover all the three primary regions of the visible light, and you can have laser sheets coming from such applications. There are welding masks. I don't have time to discuss this. I will skip this and I'll go to something wherein we are creating now lenses, adaptive lenses. Sorry, again, no details except to show one thing that people are doing it for developing world, including Africa, Asia, and Latin America, where there is a huge demand for new kinds of glasses that can tune themselves to the kind of either myopia or hypermetropia, or which I mean short sight or the long sight problems that people have. These are kind of statistics that are provided. Eyeglasses, the need versus distribution. Asia, there is a huge need every year. 1.6 million every year they need eyeglasses, but only a very small portion of them are given the glasses because of the kind of affordability and all that kind of thing. So newer kind of technology is coming in where tunable lenses can be given. And this is a very simple mechanical kind of tuning that can give an ordinary eyeglass the entire power of what you have in progressive glasses, but at a fraction of a cost, at much lower cost, you can get that kind of a thing. But this is only mechanical focusing. But what we are doing in leucocrystals is to take it to a much higher level. I won't spend time on this. Is to have a curvature built into leucocrystals, and again electric field application. And now you can have switchable lenses by applying a small electric field, which are comparable to the electric fields present inside the human body. You can change the focus, and so therefore, by putting one lens inside your inside the eye, you can make the person view anything, either an extremely fine object which needs all kinds of objects like a magnifying glass, etc., or to view something which is at a distance without wearing additional glasses. And so therefore, these are adaptable lenses. They tune themselves to the kind of scenario that is being used. I'm sorry, I can't be explaining this into too much. Dr. Yelamuga has already explained something about lytropic leucocrystals. I want to just refresh our memory into that. These lytropic leucocrystals are made of two contradictory requirements, something that is hydrophilic, which means water loving, and something that is hydrophobic, or water disliking portions. These are actually like these kinds of chemical structures, so they like water. These are actually like wax molecules. They don't like water. As you know, wax doesn't like, or grease doesn't like, or oil doesn't like water. So covalently they are linked and they form the lytropic liquid crystal molecule. And when you disperse them in water, Dr. Elamagad again was talking about how water is important for us to form lytropic liquid crystals. And so therefore they come into our rescue to form beautiful structures because of this hydrophilic and hydrophobic interaction. If you disperse them in water, they form such what we call as them self-assembled structures. They come in a variety of such structures possible. So therefore, if you have such structures, I won't spend time. I'll come to the application of that. Shampoo is a beautiful example of such structures. I won't get into the details of how shampoos are made. It's a big industry. It appears so simple, but it's a big industry. And the person who actually delivers, giving you beautiful shampoos, something that cleans your hair very well, actually has to worry about a variety of parameters. Some of them I have listed out here. He or she has to worry about a number of them, but still keeping the cost low. So therefore, it's a very challenging job, but the end product is what we are going to look at, because we demand after using the shampoo, it should be ease of combing should be existing, luster of hair, hair should look shiny, speed of drying should be there. Quickly you have to dry and then rush to your movie, or ease of combing, and then safety of the shampoo. It should not chemically hurt the skin underneath. And it should, of course, clean up the hair very well. And it should have the wettability aspect, which I'm not going to touch upon. So how does it work? It works on this principle that is shown here. Ma'am, after this, I have one more simple video, and then I'm done. Imagine this yellow strand is the hair strand that you have. On top of it, there is a dirt patch. Dirt is nothing but grease on which dust has settled, let's say. And what you see around as the blue patch is water. And inside that, now there are shampoo molecules like the one that I showed earlier. You have a hydrophilic part which wants to be with water, and there is a hydrophobic part which wants to be away from water. And so now when you have such a scenario, please remember this grease is nothing but a hydrophobic one, and this hydrophobic part of the shampoo wants to be with grease because both are hydrophobic. And so therefore they organize themselves to be on the dirt patch like that. And this hydrophilic part wants to be with water. So they mingle with water. These hydrophobic parts of the shampoo, they hold on to the dirt patch, and this hydrophilic part gets washed away with excess water and cleans the dirt that was existing on the strand. Of course, using a conditioner is a different aspect here. It has nothing to do with liquid crystals. But just for the sake of it, let me mention what is the job of the conditioner in a shampoo plus conditioner that you buy when you go to the market to buy such a shampoo conditioner. I don't have to worry because I hardly have any hairs left on my head. But youngsters, you have a lot of hairs. And nowadays, even youngsters start getting baldy. But you don't want to show up when you go with your friends that you are getting baldy. So you want a lot of hair to be making the appearance. But since of the thinning of the hair means also that there is a density that is reduced. So what you want to do is increase the volume of hair. And now beauticians talk about volume of hair. And this is done by putting the conditioner. And this is something that actually you have learned as students of electrostatics. You would have learned that like charges repel, unlike charges attract. So therefore, what they do is in a conditioner, they make the strands have a certain charge. And the shampoo actually comes with a certain charge that gets deposited on the hair strands. But now two strands are charged with the same kind of charge. They have the like charges. And so therefore, when the two strands, neighboring strands are charged with the same charge, they want to repel and then go away. And so therefore, the hair strands, since they are repelling, they give you a feeling as if there is more hair or as if there is more volume of hair. But of course, with time, the charges dissipate. And so therefore, you go back to the same kind of semi-baldy condition that you have. But at least the time that you have the conditioner on your hair, the volume actually appears to be large. So this is the shampoo plus conditioner. The shampoo appeals to the liquid crystal character. The conditioner actually is purely electrostatics, that is controlling the volume of the hair. In fact, the same principle is used in biosurfactants also, and to clear oil spillages. These are petrol, for example, a tanker carrying petrol. If it gets spilled over, it's a very serious problem. It is not that you have lost so much of petrol. It is because the organisms that live, the aquatic organisms, cannot be living in water that is containing the petroleum. Their breathing and their other habits actually get seriously affected. They die. So therefore, oil spillage is a very serious problem. It has to be contained in a very short duration. And the same biosurfactants appeal to the same kind of liquid crystal physics that I talked about by appealing to the hydrophilic, hydrophobic interactions, and they can serve very well for cleaning up such oil spillages. I'm done. The last part actually is something that appeals to something that you did years ago, wearing a uniform, and on Saturdays perhaps, or Wednesdays, when you were wearing your white uniform, when you came home, mother used to be very angry because textiles actually shrink, they fade, they stain, they add, they color, they wrinkle, and all that kind of a thing. And mother was never happy with your white dress when you came home after school. It's because of these problems. So is it possible to create a textile which appeals to the kind of interactions that I talked about, hydrophilic or hydrophobic, and then make sure that none of these problems exist? They don't shrink, they don't fade, they don't stain, or they don't create odor, they don't smell. That's what I mean. Or they have coloring kind of problems. Is it possible to appeal? That's what I want to show. I hope that the video I'm going to show works. Let me see if it works. Let's enjoy this brief video, which shows the kind of so-called super shirt created. And this has that special property that any stain doesn't stay on the textile, on the shirt that is created. So let's see whether the movie works. These two are employees of the company which has made this super shirt. They are boasting about the qualities of the shirt: stain resistant, collar is very flexible, the cuffs stay very well, you don't have to keep ironing them, no wrinkles. And this person, the male, wants to take a nap. He's taking a nap. This girl is very naughty, so she pours wine. As you know, wine stains are difficult to clean. If you don't know, you may ask your elders. But you see what has happened. She just wipes it off with a piece of cloth and the stain is gone. This is something that you would know. Ketchup, for example, ketchup stains are difficult to clean. But now, this is an ordinary piece of cloth, wine and ketchup. You see, it is not cleaned up at all because ordinary cloth is not hydrophobic. A cloth piece which is treated for hydrophobic purposes can act like a super shirt, and so no stains, no wrinkles. You don't have to be worried about mom complaining when you come home from school. You would have played with your friends in the playground and elsewhere, etc. And so therefore, it would have become dirty. But with the hydrophobic or with the super shirt material, this is no more true. So therefore, liquid crystals come with a variety, a number of applications. I have to apologize, I could not cover a number of them still, but I tried to give you a flavor for the kind of applications that liquid crystals can be employed for. And thank you very much. Again, sorry, let me not. I pressed in the wrong place. Thank you very much for the opportunity to talk to you people. If there are questions, I'm certainly open for them. And if we don't have time, I have put my email here. You can always write to me. And I enjoy talking to people about the kind of questions that they have on the kind of topics that I have talked about today. Don't send me a question about black holes or astronomy or why the bridge collapsed elsewhere. Talk to me something about liquid crystals and its application that I discuss today. Thank you very much again.
Thank you, sir. Thank you so much for such a wonderful presentation. Students, if you have any questions, please ask them quickly. Sir, this is the day of instant feedback, sir. If you can see the chat box, it's full
I am
of
seeing
people.
chat box, ma'am, but I'm trying to go down and then see what
So
are there
many
questions
are
or just patting on the back?
Yeah, it is very much patting on the back and instantaneously without any prompting student. That means they are completely, satisfied, sir. You have ignited that curiosity in their minds. What an array of multi-dimensional technological applications of liquid crystals, especially in their area of interest with mobile phones and fog on demand. Unbelievable, sir. Thank you very much for this wonderful presentation. Can't forget it soon. We have taken quite a few screenshots also to keep reminding us about those things. I request Ms. Saumya Kulkarni of 6th semester BSc to propose a vote of thanks to you formally, sir. But informally, everybody seems to be full of thanks to you. Over to Saumya.
Thank you so much.
Good afternoon to all the shareholders here. I would like to thank today's speaker by saying a quote, that is, the influence of a teacher cannot be erased. I, Soumya, here before you to shell out vote of thanks on this marked event. So, on behalf of PC Jabin Science College, I predominantly thank today's speaker, Dr. S. Krishna Prasad Sir, scientist, Center of Nano and Soft Particles Materials, Bangalore, for illuminating us by his extravaganza words. My heartfelt thanks to our beloved principal, Dr. L.D. Horkedi Sir, for his passionate support. My special thanks to all the deputies of Chemistry Department for emboldening us. Lastly, I would thank all the shareholders in this conference to make this event a smash hit. Thank you, ma'am.
Thank you very much, Saumya. Thanks a lot.
I should have perhaps added that probably the college is also enjoying a particular aspect because you have given us a new chief minister.
Yes, sir.
Yes, sir. Yes.
Thank you, sir. Now, like they say, no, sir, it's though a cliched statement, all good things have to come to an end. I just cannot understand how these 2 days have flown by with so much of information, and more than anything, the curiosity and the interest and the wonders, the awe, where the scientists have gone, what have they taken over. This is one aspect of science, children. You imagine the areas of science and how much you can contribute. You can easily become the top of the world, like our sportsmen and women are showing today. We are waiting for students of PC Jabin Science College to do some wonderful things. And you have mentors, in your own city who are completely ready to help you. You should take advantage, reach out to them, ask them, take their directions and move ahead in life. This should be a platform. This should be a take-off board for you people so that you can really reach out. These seminars are not just done for adding, numbers to our presentations at the end of the year presentation. No, these are the ones which the purpose is to ignite that interest in all of you. Hope that we have achieved in that area. To tell you very frankly, I think I must start my vote of thanks to 3 extremely great organizations of this country: Center for Nano Soft Matter Sciences, Bangalore; Royal Society of Chemistry, local section Deccan. Actually, for the information of all the people who are sitting here, I would like to say local section Deccan includes Telangana, Andhra Pradesh, Karnataka, and Goa. So these are the areas which come under the ambit of local section Deccan. We have been doing a wonderful job. I hope you people will join in our army and help us take it forward. And of course, KLE Societies, PC Jabin College, Hubballi. From yesterday, you are not stopping, to make me wonder and, impress me day by day of how good your college is and how good your students are. Thank you very much for combining our efforts to put this forward. And this would not have happened if it wasn't for, at the risk of sounding, repeated, I would like to thank Dr. C.V. Yellamgad for initiating this, for Dr. D.S. Shankar Rao, along with their director, Professor B.L.V. Prasad of CENS, Center for Nano and Soft Matter Sciences, Principal Dr. L.D. Horakeri sir, and definitely the person behind the show, Dr. Samrani Patil, and her entire team. The captain and the team, the captain of the ship is as important as the crew. So all of you have done an excellent job, madam. Very, very grateful to you. So the principal of your college, your chemistry department, the head of the department, the convener of this program, great thanks to all of you. I definitely would like to thank Professor R.B.N. Prasad, Chairman, Royal Society of Chemistry Local Section, Deccan, Professor V. Pisapati Garu, Special Advisor, Royal Society of Chemistry, and then Dr. Sri Lakshmi, who is the Treasurer, Dr. Pintu Ganguli, who is Vice Chairperson of this Royal Society of Chemistry, and our very useful and extremely vibrant and resourceful executive committee member, Dr. C.V. Yellamgad, for having, this program and going ahead with it. From CENS, I would like to thank each person, Professor B.L.V. Prasad, for showing so much of interest and, sir, investing so much of resources, sir, both man and time. Thank you very much for this investment, which is going to heap rich results among the students. You will see the difference, I'm sure. Dr. H.S.S. Ramakrishna Matte Garu, Dr. S. Krishna Prasad Garu, and of course, Dr. D.S. Shankar Rao Garu is a coordinator, outreach program of CENS. Thank you for your resources, sir. Thank you for your time. Thanks a lot. I hope that we will do more of this and expose more students of our country to this kind of, what an array. I myself am impressed, so I can imagine how students must be impressed. What an array of applications, sir. How impressive was the presentation. I think more and more students should see it's not enough they see 2-3 people as scientists or sports person. They should also see people like you who are working, incessantly behind the scenes, without, whether it is COVID, non-COVID, day and night, you people are working. It should come into the forefront, in front of the media. I hope that our media people will wake up to this and see that more students be exposed and give them that, inspiration, that kind of encouragement to come up and do better. Again, I thank PC Jabin College entire staff, Principal Horakeri Garu, Head of the Department, Dr. Patil, and the entire team, and definitely the students. Thank you very much, students, for your patient listening. You have been extremely fortunate, I should say. I need not thank you actually, because it's a mutual, it was a symbiotic movement here for the last 2 days. Take full advantage. Wish you all the best. God bless you. Now I request Dr. Srimati S.M. Patil Garu, convener, head of the Department of Chemistry, PC Jabin College, to say a few words as concluding remarks.
Thank you, madam. Respected resource persons, organizers, and all my dear participants. I, Srimati Shishikala Patil, HOD Chemistry of PC Jabin Science College, Hubballi, deem it a great honor and privilege to propose vote of thanks on this memorable occasion. First, I thank our special resource person of today's first session, Dr. C.V. Yellamgad, scientist, CENS Bengaluru, for enlightening all the participants on the topic liquid crystals, the unique soft matter, its fundamental aspects. Sir, its basic properties you have elaborated of liquid crystals, soft nanocomposites, supramolecular fluorescent discotics, plasma as high energy phase of matter, Bose-Einstein condensates, unique properties of liquid crystals, and so many other properties which are very important to be understood by ourselves as well as our students. Sir, it was an excellent session and very motivating, so that students will learn in this direction and motivate to take up in any aspect of the study of liquid crystals. In the second session, my special hearty thanks to Dr. S. Krishna Prasad, scientist, CENS Bengaluru, who enlightened us on multidimensional technological applications of liquid crystals. Sir, you have a very, very high, huge knowledge of this subject because you have worked so much on that. Hats off to you, sir, and we are blessed to have you today. Sir, you have emphasized on soft matter, all physico-chemical systems that have large response functions related to bonding in the glues, the paints, the soaps, all our daily usage materials. And you have mainly stressed on the thermotropic LCDs, liquid crystals, lyotropic liquid crystals, the elastic deformations, the use of these in the LCD TV projectors. Especially our students have enjoyed all these applications in day-to-day life, which you have emphasized, and they have also understood the huge applications and the techniques as well as the basic properties of these daily usages of liquid crystals and their multidimensional technology involved in it. Thank you very much, sir. I thank Dr. Srimati K.R. Radhika, Madam, Secretary, RSC, Local Section Deccan, for the concluding remarks and for effective and systematic conduct of 2-day seminar. Thank you very much, Madam. I thank all the participants for making the 2-day seminar successful on huge applications of the liquid crystals. I thank our principal, Dr. L.D. Horkeri, sir, for supporting us with all his help. And I thank my technical team of staff members who have handled these sessions, the 2-day sessions, systematically. I thank heartily with pride the joint venture of Royal Society of Chemistry, UK, Local Section Deccan, India, Center for Nano and Soft Matter Sciences, Bengaluru, and KLE Society for jointly organizing the 2-day online seminar on nano and soft materials for societal needs. I thank one and all present here, all the participants, the students, the faculty, everyone for making this seminar, the 2-day seminar, a successful one. Thank you one and all. Thank you, sir.
Sir. Thank you, sir. Thank you, Yellamgat, sir. Thank you, Krishna Prasad, sir.
Thank you.
Thank you very much.
Thank you, madam.
Thank you, sir.
Thank you. Bye. See you.
2 days, sir.
Yes, sir. I wish both of you will visit our college when everything eases.
It would be a pleasure. In fact, I don't know whether it has already been mentioned. We have a very strong outreach program here at the center.
Yes.
Under normal circumstances, we would have right away invited a selected band of your students who are quite interested in such things to visit our center, go through our labs.
Yes.
We have such regular programs. I don't know whether Dr. Shankar Rao has already mentioned them yesterday. So if not, please go through the outreach aspects which are put on our website, on our center's website.
Yes.
And certainly students who are interested can take up some of those activities. And certainly
Yes,
teachers are most invited to be part of it as well.
Definitely, sir. We'll visit, sir, with our students.
Yes. I think
so. Welcome.
Thank you, sir. Thank you.
Bye.
Sir, I just was asked by one college in Hyderabad, sir, that they would like to visit places like yours, but with COVID and it hovering over our heads, it is such a sad thing that children are really suffering in this. But I'm sure this kind of exposure will bring some hope to them, sir, some interest and some looking forward to in life. Thank you very much for your contribution, sir. Thanks a lot. Words will never be enough to express what we actually feel.
Kind of you, ma'am.
So much.
Definitely,
I enjoyed the workshop.
Thank you, everybody.
Thank you.
Thank you, Mahanti, sir. Thank you so much for being there throughout. Thanks a lot, sir.
Thank you. Thank you.
Thank you, madam. Thank you, madam.
My
Please
special
visit.
thanks to principal
Yes, sir. Yes, sir. Yes. Yes, sir. We'll reach him.
Please convey
Thank
our
you.
thanks.
Definitely,
Convey our
definitely.
thanks. Mahanti sir, you have been there throughout. Thank you very much.
Thank you. Thank you. Thank you.
Thank you.
Thank you.
Namaste.
Thank you, Madam. We shall leave. We shall leave.
Yes, sir. Yes, sir. Thank you. Sorry, call my close one. This one.